Hi everyone, and welcome to this community event. I'm Sylvain, a research engineer at Hugging Face, and I've led the team that developed the Hugging Face course. We're very excited to release part 2 of the course today, with content that should help you tackle any NLP task. You can check it out at huggingface.co/course, and it's going to look like this. I'll co-host today's event with Lewis. Lewis, if you want to introduce yourself.
Sure. G'day everyone, I'm Lewis and I'm a machine learning engineer at Hugging Face, and I've been working with Sylvain and the team to build the content for the course. And today I'll be also taking part in introducing the speakers with Sylvain. But before we introduce the first speaker today, I'd like to sort of show you a bit how we're going to do the question and answering. So I'll share my screen and you should see the Hugging Face forums. So even though you can probably see us on YouTube or Twitch, we're going to take all of the questions on the forum. So what you want to do when you're watching one of the speakers is you head to the course category, and then here you'll see various topics for each of the speakers. So the first speaker today is going to be Tom Wolf, and the way it works is you post a reply to this topic. So you can say, "Hello, I have a question." And then once you post this, people can vote on that topic, and we'll then select the most voted topics by when you click a like. And this will then allow us to rank the most important questions that you have. And it will also let people who can't make it today for the live stream also benefit from all of your awesome questions. So with that, I will head back to Sylvain.
So our first speaker today is Thomas Wolf. Thomas Wolf is our very own co-founder and chief science officer at Hugging Face, and on top of creating many popular libraries like transformers and datasets, he is also the initiator and senior chair of the largest research collaboration that has ever existed in artificial intelligence, called Big Science. And today he will talk to us about transfer learning and the birth of the transformers library. So, Tom, ready when you are.
Thanks a lot, Sylvain. Okay, hi everyone. Today I'm very happy to make a talk a little bit different than what I do usually. Since you will learn a lot of things in the coming course, right? This is a full week of classes, a full week of chapters to read. So I thought I won't do an educational course like I do usually, but I'll actually talk about the origin of Hugging Face and the origin of transformers, the origin of our library, and kind of walk you through a very personal, honestly, selection of what happened in the past few years at Hugging Face and in the field of transfer learning. So let's go back in time to the very beginning of why we're here today, at least why I'm here today, which is 4 years ago, 5 years ago now. October 4, Qian, who was an old classmate of me, we were playing music together in a kind of progressive rock band, kind of talked to me about the coming revolution of deep learning and say, okay, you've been doing a little bit of science at before doing your law degree. Do you want to come back to doing some science? And I was like, yeah, actually, yeah. And so we followed together this Stanford CS224D Deep Learning for NLP class, which was a lot about LSTM, skip thought vectors for those who were already following a little bit. And actually, this is, I think, interesting because today we kind of back to this, right? We're doing a course. At that time, also, we followed that over the internet. There was still no pandemic. It was easier, but still the course was at Stanford. We were both in Europe. And so maybe today, some of you will be following this class with friends, maybe friends in the music group band, or I don't know. And maybe in a few years, we will have a very successful startup that started this week by following this course together. And that's really all that I hope for you. I think for us, it's been an amazing journey from this day to today. And the early days of Hugging Face were actually quite different than the Hugging Face we know today. We were building an AI chatbot that was a little bit like a talking Tamagotchi. you could like discuss with it. It was the beginning of generative technologies, right? All with LSTM. And you could also send it selfie. There was beginning of image classification to try to understand a little bit what you were sending and to try to reply with something fun. And that's how Hugging Face started. We were just 3, 4 at this time. But quite quickly, we actually started to open source a little bit of code. So this is a screenshot from the Hugging Face GitHub pages 4 years ago. You can see probably libraries and framework you don't know because they've changed a lot, but it was the first one. We were really proud of our coreference Pytorch adaptation of an emoji detector, of a like sentimental detector. But why has this all completely changed? Because there was a couple of revolution in the field of NLP a few years after we started, so more precisely around the beginning of 2018, I would say. So I think if you want to date back, this could maybe go back to this first unsupervised sentiment neuron paper from Alec Radford already at OpenAI, where they trained an LSTM on the largest data set that people had at that time, which was data set of Amazon reviews. Well, actually, the internet was already there, but still not common practice, right, to use that as a training data set. So they trained this LSTM, and what they discovered is that the model, the LSTM, learned to actually categorize sentiment without being explicitly taught to do that. So this was trained in a generative fashion. This LSTM was trained to generate the next token, just like we do today, right? And they also identified, well, something that we don't really use anymore today, I would say, but some specific neurons that were very finely tuned to detect sentiment. And so this was the first hint that unsupervised pre-training with a generative objective could lead to good performances on downstream tasks like sentiment classification. But this was still using LSTM, and the data set was still quite, I would say, domain specific. Amazon reviews are still not, I would say, as widely as covering a wide field of NLP as the data set that we have today. So a bit later, I would say at the end of 2017, so a few months later, were the first, I think, most impactful paper, which was this first ELMO, which is the first this paper called Deep Contextualized Word Representation. That was the ELMO, the beginning of the Muppet names, right, for all this model, which kind of showed that if you pre-trained on kind of an LSTM on a wider diversity of text. So this one was unfortunately using a shuffled text. So it only had like full sentence, but not full paragraph. You could actually have good performances on a lot of NLP tasks, and not only sentiment analysis, but also like question answering, textual entailment, and this kind of thing. The idea here was still kind of to extract token representation, more than maybe what we do today with like full pre-trained model. And then really concurrent to this work was the very nice ULM fit from Sebastian Ruder and Jeremy Howard, where they also pre-trained this LSTM, and they also showed that you could adapt it to many, many tasks. So these two papers really at the same time, at the beginning of 2018, people were like, oh, maybe all this approach of transfer learning that we've been using in computer vision on ImageNet for a long time could be useful also in text. And so this kind of led Sebastian to write this interesting piece in around the summer of 2018, which was maybe the ImageNet moment of NLP has arrived, right? And he was very, I think, insightful in saying, oh, pre-trained language model can achieve state-of-the-art results, and that's something that's going to change everything. But this was just one part of the revolution, which is transfer learning, pre-trained model. And the second part was using transformers in place from LSTM. And here again, I think Alec Radford from OpenAI was really pioneering this by using the GPT, the first GPT in 2018. So this was around the summer with this generative pre-trained transformers. And actually, the name really GPT was, I think, only coined in the following BERT paper from Google, which was a few months later in October 8, 2018, where they kind of used this same transformer model, but instead of using it as a causal or autoaggressive model, they used the now famous masked language modeling objective, right? Denoising objective. And so these two papers were very interesting because they mixed this early idea of transfer learning, like having a model pre-trained on a large data set, with the architectural improvement of the transformer, which made mostly the training very efficient, a lot more efficient than LSTM. Though today we have like other, well, maybe we're coming back. I'm not sure. This is maybe what you will be in charge to do if you do research in this field. And what was the conclusion of mixing these two objectives? Well, it was really a storm in the NLP field. So you can see this if you go, for instance, on paper with code. If you check this curve showing the state of the art at various time, what you see is that in around the end of 2017, beginning of 2018, you see this very strong slope upward, right? There was like performance was basically plateauing for like years, right? Here we see that on NER. Since basically 2009, we did not really move up anything. And then from like summer 2018-17, TagLM was already kind of a first transfer learning approach, actually. And then with Transformer, we were moving upward very strongly. Squad 2, you see also the same very strong increase in the performance of the model by using BERT. You see the jump BERT single model. There's a very strong jump, 10 points in exact match here, metric. And then, well, you can say maybe we're plateauing again today. I think most of the reason we're plateauing is that Squad 2 is now kind of saturated, actually, as a benchmark. And so we were following that very closely. And basically, when GPT, the first of the names, so this one, went out, we were actually at Hugging Face participating in a challenge at NeurIPS. Well, this is an old slide, so we still call it NIPS, but that's now NeurIPS, right? 2018, we were participating in this conversational AI challenge. So the goal was when you have some sort of chatbot, you had to like take into account a little persona for your robot, and you have to answer in a convincing way to a user. So it's a little bit like a Turing test, right? But you have a persona. You're supposed to pretend you're this person here. And this challenge was interesting because it came with a nice data set made by the New York Facebook team. And for this first time, GPT was just out, and we were like, okay, maybe let's try this GPT. Let's try this pre-training approach for generative tasks as well. A lot of people were just using this model for classification tasks. And so we tried for the first time to use it for really purely generative tasks like chatbots. And the results you can see on the right were really impressive. We were directly on top of the leaderboard of the competition, and by a very strong margin. The perplexity, the first column, we were like, perplexity is a kind of an exponential metric, so it's quite hard to divide by 2 the perplexity, but we were like 2 times lower than the other model. Well, these metrics, well, if you've done a little bit of generative NLP, and you will learn that in the course here, it's very hard to evaluate. So this did not translate always in human evaluation, but it was still already very, very, very impressive. And when we studied a little bit and compared to the other teams, what we saw is that if some team were very good on the validation set, they often went very down on the hidden test set. So if you've been doing a little bit of Kaggle, you know that this mostly means that you're starting to overfit on the validation, the public data set. And some teams were a bit lower and staying lower, right? Which is more like a sign of kind of underfitting, if you want. And what we saw is that our approach was both using transfer learning and transformer as well, but transfer learning, I think, is the strongest ingredient. Using transfer learning, we were both very strong on validation sets, and we stayed very robust on the test set. Hoopla. And so this led us in the next summer, in June 2019, to do a very long tutorial around transfer learning in NLP with a few friends, Sebastian Ruder, Matthew Peters, who basically created this field, Swaba, who also actually did really great stuff I won't show here, but you should check them out. And what we saw there, well, what we tried to do there is try to explain a little bit what was the idea. And so just as an insight, you will learn more in the course, but basically this is the secret ingredient of transfer learning, is that in traditional machine learning, we had all these separate tasks. This is on the left. You had task 1, you wanted to do NER, you had a data set for NER, and you basically randomly initialize your model and train it from scratch on this data set. If you are now trying to do summarization or chatbot, you will gather another data set of summarization or chatbot, and you will, again, just create a machine learning system specialized for this task. And if you had another task, again, same thing. You will have very separate pipelines, very separate systems who are already, each time trained from scratch. And the approach of transfer learning was to do a little bit more like, I would say, humans do, which is that we don't randomly initialize our brain each time we tackle a new task, right? What we do is that we use all the knowledge that we've learned in the class, in our life experiences, to bootstrap our learning, right? And so when we have a new task, we just reuse all this knowledge that we have. And this gives us mostly two main advantages that we see also when we reproduce that with machine learning models, which is first that we are very data efficient, because we can fill the gaps between all the examples that people are giving of a new task. And so we are very data efficient, and we usually reach better performances. And this is also related because we can fill the gap between the data examples that we have on the new target task. We can reach better performances. And transfer learning is a way to try to do the same for machine learning. So to try to build this kind of generic knowledge that can be reused on many, many tasks.
So we have questions that could go here, Tom. Is there a systematic way to estimate how many annotated samples to fine-tune an existing model, for instance, on an R task?
Yeah, that's a good question. It's quite dependent. So really the direction the field is trying to go is toward what we call few shots. So using less and less examples. So I mean, requiring less and less examples. So for some tasks that you will see in the course, you can actually do 0 shot, like text classification. You actually, in many cases, don't need any example. But then it's always very dependent on how specific your domain is. And typically, the more specific your domain is, the more you will need example. And in some case, you might still be outside of the pre-training domain of the model, and then you will need quite a large data set. Yeah.
Thanks.
And so, let's go. Yeah. Why would this work in NLP? Well, you probably have the intuition, but here they are. The idea is that many NLP tasks, if you take a step back, they share a common knowledge about language. They share that. Let's put that back in full screen. Yeah. Basically, if you know, for instance, adjectives, if you know linguistics, then it will help you a lot. For instance, if you want to do NER, right? You want to identify, the name of organization. If your model already have a good knowledge about linguistics and know what is a noun, that will help it a lot, because it will know that name of organization are very likely nouns. Okay, they are not adjectives, they are not verbs. So all these things can be useful for the model. The same, right? If your task is in English, if your model know a little bit about English, it can just learn basically the missing pieces that it has on your task, and won't need, I would say, like half of your training data set just to learn how English works in general, right? So tasks can also inform each other. Typically, as I told you, syntax and semantics, they are often related. If something is a noun, that's also mean that it has a meaning related to a noun. If it's an adjective, that's here to kind of change the meaning of a noun. So all the thing. Obviously, annotated data, that is rare. It's very difficult. So the more we can gather it, the more we can gather several data sets together to build a bigger one, the better it is for our model. We know that these neural network models, they are still data hungry, right? We don't have a lot of feature. That's the nice thing about them. But the counterpart is that they are data hungry, because they will need to learn this feature themselves. And now the most I would say, a down on earth reason why it works is that when we try, it works. So that's currently the state of the art for many NLP tasks. It's to use this transfer learning. So that's also a good reason to think that, well, maybe it has reason to work. So I talk a lot about science here, like transfer learning revolution is a scientific revolution in the field. But if you're here today, it's also because you've probably been following our open source work. And this was kind of started in parallel to that. We always thought that open source and open science were going hand in hand. And so very early, we started to open source some models. So the first one we did is here. It's now the summer of 2018. So just before basically this transfer learning revolution really began. And so we did this neural coherence, which was a coherence model for SPACY, which already show very interesting performances for also a pre-trained actually neural network, but only for coherence. And then there was obviously this GPT. So I told you we were using the first version of GPT in this first competition, and that's where basically we understood that, wow, this was very powerful. And before using it, as always, we actually released an open source version. So actually a bit later, we discovered that some other competitor also used our open source GPT in the same competition. So it was very, very interesting. We actually made a paper together at ACL a year later. So it's a bit the open source way of Hugging Face, always trying to do something collaboratively with everyone. I think that we can just get the sum of every open source thing is larger than having just everything private models. And these two early efforts and the interest we saw from people led us to try to do that again. And this led us to the first stone of transformers, which was this conversion of BERT in Pytorch. So in October, there was this BERT model from Google, and people are like, wow, this is really an impressive model. And so when the code was open source in TensorFlow 1 at that time, we thought, oh, that's a little bit a shame because TensorFlow 1 is still a little bit difficult to use, right? And there was Pytorch already at that time. It was Pytorch version 0.3, but it was still quite interesting and easy to use. And so we decided, okay, let's convert this TensorFlow model in Pytorch and let's see if people will be able to use it easier, right? And our idea here was basically that, well, first at that time, BERT sounded like a very large model. It was 300 million parameters, which today sounds like maybe the smallest model that you use, at least in the research field. But at that time, it was like really, really large. And so we're like, nobody will be able to train that. So we should make it easy to use the pre-trained weights that Google really nicely released. And to make it the easiest, we should actually have them also in Pytorch. And so that's what we did. And that led to this first version called a Pytorch pre-trained BERT. And this was really very far from transformers. But we had a few initial ideas that evolved. So one initial idea was that we could also host the pre-trained weights on our S3 buckets so that people didn't have to go through the painful process of downloading and converting them, and we could maybe just load them. And here we were inspired by Joel Grus's nicely made from pre-trained method in AllenNLP, which I found very, very nice. With just one line of Python, you could download a pre-trained model in AllenNLP. And so I was like, okay, let's actually use the same idea. And so this was the first thing. And this evolved over the coming 2 years, I would say, from 2018 to 2020 to a fully fledged Git version model hub that you will see today, which both, I think, give you very wide access to the model. It's very easy to inspect it, and at the same time give you a lot of interesting like widget to play with the model, online API to use it very easily. So all this you will see in the class, but that's very interesting. And the first idea was also just to give access to BERT, right? But then I was like, okay, we actually have an open source code for GPT, another for BERT. Why not actually make them in a single library? And this led us very quickly to basically a single API, which today I think wrap not far from 100 different architectures, which is the today transformers. And so the first version was Pytorch transformers with 4 architectures. And quickly we thought, now TensorFlow 1 is a little bit hard to use, but TensorFlow 2 is quite nicely done, actually. And so you're like, maybe we could have both Pytorch and TensorFlow 2 in the same framework. And maybe we could even make it this, so if you want to use TPU to train your model on TPU because you have like free access, you should. And then if you want to fine-tune the same model in Pytorch, you should be able to switch very easily from one to the other. And so we tried to make these two main framework at that time, and then later JAX and Flax, which are more recent, in the same framework. And we saw that it was actually not so difficult to get them all together. And to get what is now transformers, right? Not anymore Pytorch transformer. Well, Pytorch is still, I think, maybe the better supported one, but TensorFlow and JAX are very, very strongly improving. And so this was a transformer. And what we witness is this basically explosion in the number of architecture on model. Most of them are today in transformers because it's very easy to add new one. And so you can see from BERT, there were a lot of following work trying to experiment with variants in the architecture. I think maybe XLNet is a good example where they try to do both some autoregressive but also bidirectional way to do a forward pass in the neural network. And one question became, what is important for all this model? I mean, how do they compare, right? How do you select the model? Which one do you know you want to use? And here, I think what became also quite clear in the subsequent year was that actually more than architecture, it was actually the data that mattered a lot. So I talk about XLNet, which was very interesting as a different architecture and actually got a lot better performances than BERT at the time. And people were like, wow, we should experiment with various architectures for modifying the transformers. And this subsequent work from Facebook called Roberta actually showed that it's not so much the architecture, but just the data. XLNet was actually trained on a lot more data than BERT, and that's actually what mattered more than the architecture. And so Roberta took very basic transformers, just exactly the same as BERT, and then just trained it on more data. And they got state-of-the-art results. And this was then shown in these two other graphs, which are from the neural scaling paper. And they show that basically the architecture was, the performance were really weakly sensitive to the architecture. So you see at the top, you see this very flat curve for feed-forward ratio, this very flat curve for aspect ratio. And these are all logarithmic curves. So they actually span very large aspect ratio. And basically, as long as you stay not too far from the middle, you're pretty good. The architecture just don't really matter that much. And the T5 paper, who came out later, also confirmed this. Basically, the early transformer paper were already very close to the optimal architecture. But what's very important is this dataset, this graph on the lower left, where you see the dataset size. This is also from the neural scaling paper from OpenAI. And you see that just by increasing the dataset size, you have this very predictable increase in performances. So here, this is the test loss. So lower is better. And this actually brought us to this question, well, actually, more than architecture, what is important here is data. And so a year later, 2020, actually, or maybe 2019, we decided to do a new library around data. We are like, okay, we also need to focus on data now. And so this new library was called Datasets. Well, early name was NLP, but for a long time now, the name is Dataset. And this library also got some quite strong interests from the community. It passed the 10K stars. Well, I don't know how GitHub stars are relevant as a measure of interest, but it's also widely used by a lot of other work. So I think it's very nice. And this library, the idea was access to data is also very difficult today in NLP, mostly because the situation is very fragmented. If you want to use a data set, you typically need to find where is the code somewhere on GitHub. You need also to pre-process it, and you actually spend a lot of time doing the same work to pre-process the data set. A lot of people are just writing their CSV or JSON loader, so maybe we could share this work and avoid this and just jump to the data structure. That was one note. Another one was that also with this very large language model, we're using now terabytes of data. And this can be very difficult to handle at least on your personal laptop, right? If you want to train a model on 1 terabyte of data like Roberta, this is really a pain because you typically can't load that in RAM. You need to find a smart way to do like just loading the current batch or prefetching. And so we thought maybe we should solve all these issues at the same time. And the idea was that dataset could be a way to kind of centralize access to NLP dataset at the beginning. Now it's expanded to speech and images, but at the beginning it was really about NLP dataset. And also to cover more languages, right? NLP, English, I mean, is really the dominant language in research, but in production today, it's not dominant language, right? We have a lot of other, well, it's still the dominant language, but we have a lot of other languages that are very important. And every time you're actually an NLP person working in another country than the US or UK, basically or India, you want to work with other languages. And so this led us to developing dataset around this effort. So at the end of November, 1 year ago now, November 2020, we did a first community event where we said to the community, we're 15 people at Hugging Face trying to add dataset. If you want, you can join. This is going to be fun. We're going to do this together. You will be on our Slack. We'll talk a little bit. And also we'll do some swag and everything. And this was hugely popular. Actually, we had, I think, about 300 people joining to help us. We were definitely a little bit overwhelmed by the success of this fair community effort. But it was very nice also in terms of adding dataset in many, many languages. And the idea is that all these datasets were then very easy to access. And this could foster more research on multilinguality, I think. And so this led us also to write a paper with the whole team. And also there are also some community members actually in this paper. You see Gunjan, Bavitva, they are both like community contributor. And to submit it this year to MNLP, where I just actually won the best demonstration paper. So I think this is very typical Hugging Face thing where we do something very open source. We do that with the community. At least we invite everyone to join if they want to participate. And then we also do that as a science effort. And this all just go together to make something very impactful. And so there is today also this hub that you will see in the course where today we have about, not so far from 2,000 datasets openly accessible. You can even explore them on the hub. And so this was the 2020 effort around data. And what happened in 2021? That was open science more and big science. Well, what happened, I would say it's very personal walkthrough. So I would mean what I actually spent a lot of my time on was this big science effort. And here the idea was that maybe it's time to do very large collaboration in research in NLP. And the example, I'm a physics PhD formerly. And so in physics, when we have like very expensive things, we actually gather as a lot of like research lab and try to build them together. And one good example is the Large Hadron Collider, which is in Europe, which is a very, very large particle physics research tool. It costs, I think, 10 billion to build. And it has involved really a huge research community. And it has led to a lot of research work, like you have about 3,000 papers. This led to the discovery of many hadron, a thing like that. And so the idea was maybe it's time to do that in AI and NLP. And so maybe why? I mean, why would it be tight to do something like that? Well, again, I think because there was some, if you follow what I've been saying up to now, right, there is this idea that larger and larger data sets are something interesting, some direction we want to go. This was proved again by the GPT-3 paper that show that if you scale again the number of tokens, here you see it in green on the corpus side, and this is again a logarithmic scale. So the scaling is really like, how much is it? 6 order of magnitude? No, 2 order of magnitude bigger than GPT-2. Well, if you scale both the corpus size and the parameter size, you see like very interesting new effects. And these effects are few shots. So recently, just at the beginning of the talk, somebody asked how many examples would you need? And here in this few shot example, you can see that we just need like 10 examples to get very strong performances. So I don't remember exactly what this curve was in terms of accuracy. Maybe I think it was a classification task. But this one is just extracted from the GPT-3 paper, so you can find it back. And they have a lot of curves similar to this. They have a lot of curves similar to this. And so there was this idea: if you scale this a lot, you get some interesting new effects. And then quickly, what you saw is that there were a lot of announcements of reproduction. Naver Labs trained a GPT-3-like model for Korean. Anthropic, a startup of the Bay Area, raised a lot of money to train similar model. AI21 also trained a massive model called, I think, Jurassic. And another company called Keras also raised a lot of money to train all this model. And Eluter was also this grassroots collective who trying to reproduce. So a lot of people were trying to reproducing this. But for a diversity of reasons, we were not super convinced about this, mostly because like all these private company did not seems to be targeting like open source release. And Eluter was the only one. But there were still some main problems. So here is a few issues I see. Well, first, all these models, they are not designed as research tool. They're really designed by a company to be like private thing that they want to use for their private product, but they are not designed as research thing. So it's very difficult for academic researcher to be involved in the development of these models, right? And typically when you look at the teams who build them, they're like, yeah, they're like smaller than they should be, in my opinion, mostly because they just belong to one company, and mostly. There is, as again, a lot of environmental cost to training all this model in parallel. If they were open source, we wouldn't need to retrain them like in 60 company. We could just share one, and that would be a nice model for doing all our experiments. And there were some ethical and social issues, mostly since the very beginning of GPT. There's been a stream of paper investigating, okay, how are these very large test corpora? And we saw that they were lacking something. For instance, they were lacking representativeness of some population. They also typically have some stereotypes. So basically, it's very hard to investigate this training data set also because they are typically not open sourced. And so this called, in my opinion, for like a more open and collaborative way to develop this. And this is actually possible because if you look in public, you see that there are supercomputers that are very powerful and that are actually almost fully accessible. I mean, you just need to submit like a grant, an application to say, I need some compute times on this. And they have like almost 2,700 V100 GPU. So that's quite a lot of compute power. You can train a very large language model with that. So early this year, I started to talk with the operator and builder of Jean, which is one supercomputer located in France that we knew a little bit from earlier. And they say, yeah, I mean, come train your model basically on a supercomputer. We're very happy. So we kind of discussed a little bit internally, and then we decided that we should actually invite everyone to come join and to train this model with us, and in particular invite the academic community, which was typically outside of all these model creations. And so we filed a grant application for enough compute time to train a very large language model. And this was the beginning of Big Science. Big Science has been going on for like 6 months, a little bit more now, 9 months. And it has already produced very interesting papers. So if you've been following Hugging Face account, you probably saw the T0 paper, which involved actually 40 authors. So some of them are from Hugging Face, but a lot of them are not from Hugging Face. Some are from many universities. And so this type of papers, I think, is very interesting because it's outside of the box. So it's fully open, it's fully collaborative, and it's also show that you can outperform typically GPT-3 on the zero-shot benchmark with a model which is 16 times smaller. So now what we are trying to do is to actually increase the size to 16 times larger. So that's what we'll begin roughly next January, and to train this very large model on Jean to see how far we can go, right? With the same idea of like openness, open sharing, and collaborative effort. And so what's next for 2022 at Hugging Face? Well, there is obviously education. If we want to have a beneficial impact, we think that this is the way to start. When we talk about bias in data set, when we thought about understanding your model, knowing what is important for your model, basically, we think that we should share all the knowledge we have. There is this strong community you're all here today. I'm very happy about that too, because you've basically been following more or less what we've been doing. Open source, this is our DNA, and open science, they go hand in hand for me. Sharing knowledge. We try to keep fighting for beneficial, responsible AI. I talk a little bit about data set. This is very important, I think, to understand the bias, to understand the bias of your model as well. And basically try to make this, an inclusive place, right? And while doing all that, doing also this exciting research, when I say we scale this new model to very large sizes, we also try to have some fun and not taking us too seriously, which I think is also a specificity of Hugging Face, and why maybe we have this Hugging Face emoji, I would say, as the name of company. So welcome to this course. I'm very happy, very excited about this second chapter. I think it's very interesting. You will learn a lot. And thank you for being here today.
Thanks a lot, Tom. We have a few questions I've waited for the end because they are very general and not directly related to what you are talking about. One is, you talked about a lot about transformers, but what about using graph neural networks in NLP tasks? Graph structures could capture data with complex structures and relationships, and GNN provides an opportunity to study and model complex data representation for NLP tasks.
Yeah, that's a good question. I mean, in all generality, you could consider transformer as a sort of graph neural network. It's not sparse, though. It's fully connected, so maybe it could be more efficient. But if you look at like a transformer with sparse attention, in my opinion, it's really close to some graph neural network. In particular, if you use weight sharing, like universal transformers. I think in NLP, transformer are kind of dominant today. But yeah, as I told you, in my opinion, the main aspect of the revolution is about transfer learning, more than the specific architecture. So if tomorrow there is a more efficient architecture than transformer, then I would be happy to follow the work there and basically switch to that. Yeah, I think, yeah.
Another question we had was more about the Hugging Face ecosystem. Is Hugging Face currently becoming commercial from open source? There are many parts of API that are now paid, model training, for instance, with O2NLP. Please help me understand the portion of open source versus paid.
Oh, yeah. Yeah, so it's still, I mean, the idea of Hugging Face is, I think, somehow a very typical like open core model. So everything is open source, but you need to do the training yourself. You need to do the training loop yourself. So we do provide examples. That's actually, Sylvain has been doing a lot of work on the examples to have like an efficient training. So you have open source code to train this. And then we also provide some paid solutions, which are mostly there, I would say, to facilitate your work. So typically, if you're in a company, you don't want to wait, you don't have time to actually explore everything yourself, you want some help, then we also here to help. And then we have some specific solution around making this model very fast. And these are typically mostly interesting to companies more than researchers, because they try to lower the latency strongly. And then here, these are also paid product, because people who are interested in them are typically companies who can pay for them. So the idea is that if you're new to the field, if you're a hobbyist, if you're a researcher, you can use all of this for free. And then if you have some like specific needs, like you need to go very fast to put that in production, you need to have like very low latency because you have huge bandwidth in production, then we also here to help, but then we help with our like additional services.
That makes sense. Another question, you hinted a little bit about that at the end, but more fun question is, how did the name Hugging Face and the use come about?
Yeah, this came from our very early inception as a game company, right? We were doing this kind of talking chatbot. It was mainly for millennials, for kids or young adults. So we wanted a fun name. We also thought it would be fun if at some point we became a very big company. I don't know if we'll do that one day, but if we like IPO and then we have an emoji instead of like this very serious name that everybody has, we thought, yeah, let's give this emoji. And I think now it's part of the fun. We like a lot of people are taking themselves sometimes a bit too seriously, I think, in the AI world. So we're here to say, yeah, this is important, but having fun is also important.
And a last fun question that people were interested in is more personal. What do you use to build train models? Notebooks, VS Code, Vim, other?
Yeah, I typically use VS Code. Notebook, I'm always lost in the order of the cells, but maybe I have a bad workflow. Now, I typically use Notebook to explore data. I think it's very nicely done for that. That's the best way to explore data. And then when I train, I typically want something which is very reproducible. So I switch to something where I can git version cleanly and more like typical VS Code. Yeah.
Nice. Thanks a lot for your talk. It was very, very interesting. And I think we're ready for our next speaker, Lewis, if you want to introduce him. Oh, I think Lewis is not hearing us anymore, so that's why there was this silence.
Can you hear me now?
Yeah.
Great. Sorry, what did you say? I just dropped out for a sec.
I just said, I think we're ready to introduce our next speaker. If you...
Great. So let me add Jay Alammar to the stream. Hey, Jay.
And bye, Tom.
I think you might be muted at the moment.
Yes. Hello.
Great. So I think Jay probably needs no introduction to everyone who's here to listen about transformers. I think all of us have kind of started by trying to read the Attention is All You Need paper and gotten completely confused by this crazy architecture diagram, and then immediately gone to Jay's super influential blog post called The Illustrated Transformer, where he really nicely shows kind of conceptually how these things work. And then there's a whole series of beautiful blog posts ranging from Pandas to NumPy to BERT, GPT, I mean, the whole works. So thank you, Jay, for this amazing service you've done to the community. You've kind of demystified transformers, which is amazing. And today, Jay's going to talk to us about a gentle visual introduction to transformer models. So I'll add, yep, great, you got your thing there. And
perfect. Are we okay on audio?
All good.
Amazing. Thank you so much. That's a very kind introduction. Happy to be here speaking about transformers. There's a couple of examples on a notebook. This is a URL to it, but it's just a very simple sort of notebook to go over. To give some let's say history. These are some milestones from the history of writing. Right. So first time sort of people put drawings on tablets, and then people put language, carved their laws of an entire, let's say, society on a column. That's Hammurabi's law, the second image below. Then people started using paper, and then we have something like the printing machine or the printing press that sort of pushed the next, let's say, revolution. And books became cheaper to get, and knowledge and literacy became easier. So once you need a book, you don't need to go and copy it with your hand. That sort of changed the world. And I do have a sense, looking back at the history, that NLP, via sort of what machine learning is enabling us to do, that we could be at a historical sort of turning point. Where exactly did it happen the last 2 or 3 years, or is it going to happen in the next few years? It's very hard to tell if you're not sort of looking back into history, but I'm extremely fascinated by these sort of language models, and I'll tell you a little bit why. So yeah, just a brief bit about myself. I've been blogging about machine learning and transformers. Machine learning for maybe 5-6 years, transformers sort of since I wanted to understand the paper, and this is sort of a map that I used for me to understand the paper, and it turned out to be useful to other people as well. The blog has gotten about 4 million page views just because the topic became super interesting to people. And then I wrote about other types of transformers as well as NLP technology. So embeddings, Word2Vec, GPT-3, BERT, and I do some videos on YouTube as well to sort of explain some of these. I do work at Cohere, as sort of Thomas mentioned. We work on large language models. We offer sort of large representational language models, kind of like BERT, and large generation language models, kind of like GPT. So these are massive language models via API for people to experiment with and deploy in industry. So this is the URL, and we're hiring at the moment. One thing to allude to that Thomas mentioned is that Transformers has taken NLP by storm. But not only NLP, but also like computer vision, and it's like going out of NLP. This is the super glue, and you can see that transformer and transformer-based models have dominated the leaderboards. If you go and search on Google, so I bring up this example for people who sort of want to understand a little bit more of the current applications. So if you go on and to search on Google, and you type some words and you get some recommendations, your keyboard would give you some recommendations, but also the search engine would give you some recommendations. So let's say you search for Siri technology, you get this page, and then when you click on it, sometimes you get these highlighted sort of notes. I asked people which step in this process used a language model. And in an audience like this, I think you would realize that this is maybe a trick question, and it's in all of them a language model was used. So auto complete and sort of next word can be used via, let's say, language models. This summarization and highlighting, these are all sort of language model tasks. But there's even one that is more important, which is where sort of Google got you the results. So to give some sort of examples, yes, so some of these tasks are, let's say, autocomplete, text summarization, question answering, semantic search. And if you use Gmail, you have some of these suggested responses. That's response selection. That's also another thing that language models are heavily used for. So we're not talking about specific just research or interesting ideas. These are heavily in application right now. Just even less than a year since like one of these papers is written, it goes into industry really quickly. So this is sort of across the board: Google Translate, search, all the speech detection, and then using it in search as well. So like a year, I think, after the BERT paper was out, the Google search team said that implementing, let's say, semantic search using a model like BERT represented the biggest leap forward in the past 5 years, and one of the biggest leaps forward in the history of search. GPT-3 took the world by storm. So many interesting applications there. I think most of the team here has looked at it. So to think about transformer language models for a second, let's look at one of the developments that have changed the game. That it broke down this training process into 2 steps. One is pre-training, where a model is trained on a lot of data, and then you fine-tune it. You train it further for a specific use case. So if you want to create, let's say, a new semantic or sentiment analysis, let's say, classifier, you don't have to train a model from scratch. You can train a model that already understands English or multilingual or whatever language that you're. So this is one of the developments sort of that made these models revolutionary. The training process of a language model, and I'm here speaking about a what's typically called a language model, which is an autoregressive language model, kind of like GPT. It's trained on a very basic task, which is you give it, let's say, 3 tokens or 3 words, and you hold off what the correct word is. So a robot must obey, but you don't tell it to obey. You just give it the 3 tokens or 3 words. It will make a prediction. The model is not trained, so it will output a random output. We know what the actual output that we were expecting is. We calculate the error, we update the model, and then we do this for a lot of tokens, 300 billion in GPT-3's case. And then once you've pre-trained it, you can deploy it or fine-tune it or prompt engineer it for these other use cases. To tackle the architecture a little bit, I've always felt that it's easier to look at it as just one black box. And the initial transformer was about translation. So you give it a sentence in French, and it outputs a sentence in English. So you can visualize it kind of like this. And then if you were to look under the hood, it has two major components, an encoder and a decoder. And these encoder and decoder are made up of blocks. 6 blocks in the encoder and 6 in the decoder. That's the initial sort of transformer paper. And then these are the main architectural ideas, I think, that are good to establish first before thinking about different types of transformers. So the initial transformer was an encoder-decoder model. So that works really well for, say, things like machine translation. But also there are still models that are, continuing to tackle this structure. So it's still very useful on certain use cases. So T5, T0, that was sort of recently developed as well, is these encoder-decoder. And I think Mina, Google AI's large chatbot, is one of these encoder-decoder models. On the other hand, you have models that are trained completely using decoders. So these are your GPT models that are just like the traditional autoregressive models. And then you have BERT-like models structured using only the encoder sort of stack, and that tends to be called masked language modeling. So you have language models, masked language models, and you have like encoder-decoder transformers. So this is to orient yourself. And all of these are widely in use. A lot of them have specific tasks that they do better in than the others. Our talk will focus on the transformer language model. So this is going to be the type of model that we focus on. Another idea is how many layers can you sort of stack? How many blocks can you stack? And BERT large has about 24. GPT-2 large has about 36. So these are another aspect, let's say, of transformers. Is so you can talk about how large the neural networks inside are, but also how many blocks that you stack to get your model. So let's talk about language models. I've found that there's two really good examples to break down the components of a transformer layer. So let's think about a model that has, let's say, only one layer. If you give the model an example of this input, which is the Shawshank, and then this model is trained, so it has hopefully seen words kind of like this or phrases kind of like this before. You would be able to think that it is able to guess what the next word is. And this is a reference to the film, The Shawshank Redemption. And I tried this using the still GPT-2 example. And when you pass it the Shawshank, it gives you this completion. So it's able to actually know what word I was expecting after Shawshank. And this really explains to you one of the two major components of a transformer block, which is the feed-forward neural network. So in the training, when the model was trained on vast amounts of data previously, it is able to calculate these probabilities of words appearing after the current context that you have. So 2 words here, what would the third be? And this is a very similar, so this is not new as a technology in transformers. This is very similar to previous language models, and then 3 grams and n grams that were calculated using just counting how many times this word has appeared before sort of or after this context, and creating a probability distribution or score via that. So this is one of the two major components, the feed-forward neural network, and this is an example where it shines. It was able to sort of remember or have a calculation of what the next word would be, just judging on what the model has seen before. This is a paper from 2003 about these models and how they were there sort of previously, and transformers build on top of this. Now, the second component is a little bit more complex, and this is a great example to illustrate it. So when you say the chicken did not cross the road because it, and you want the model to complete what the next word would be. Now, the model cannot only calculate, what words usually appear after the word it. That would not produce a really good model. It would not be able to fit its data set really well. And before it sort of does that, it needs to resolve, what does it refer to here? Does it refer to the chicken, or does it refer to the road? So that ambiguity is there. And we can throw this at a small GPT example, and we can see, if we say the chicken didn't cross the road because it was covered in grass. So that's probably the road, right? He thought the sun wasn't so bad. Then now I don't know. Maybe the chicken was covered in grass and the sun was not so bad. So this is sort of a good example of this other component of a transformer block, which is self-attention. What self-attention does is that when the model is processing this token, self-attention associates it either with the chicken or with the road, or with a mixture of both. And really, that it's a mixture of the entire sentence. So that is one of the major things that transformers brought, I guess, to NLP, in addition to being easier and better to run in parallel, as compared to RNNs, which were used heavily before sort of transformers took over. So these are the two components: self-attention, which whenever you're processing a token, it bakes in its understanding or representation of that token relevant information from other parts of the input, and then feed forward, which is neural network, which is builds on top of that. The idea of tokenization is another important one. So the example that I showed you here was a little bit simplified. When I actually throw the Shawshank at the tokenizer of GPT-2 is what I'm using here, it would break it down kind of like this. So these two words would be 4 tokens. And then through the tokenizer, that would be translated into token IDs. And these token IDs will be the ones that are hitting the model. And then the model outputs something that we can translate into a word using the token again. And so if you're to work with BERT or GPT models, these are the two, let's say, components, pieces of code that you'll have to deal with. The tokenizer, which translates between our words and, let's say, token IDs, and the actual model, which has never seen any words, has only seen token IDs. So I'll leave you to be able to go through the notebook. And this is sort of an interesting idea that I thought. So GPT-3, this was one of the, let's say, outputs of GPT-3 saying, to be clear, I'm not a person, I'm not self-aware, I'm not conscious, I can't feel pain, I don't enjoy anything, I am cold, calculating machine designed to simulate a human response. So this and other sort of interesting generations from massive language models are very interesting if you can think of them as, these were outputted by a machine. Now, definitely should be suspicious until you see sort of what the prompt was, but it's still interesting. But what's more interesting is that the model has never actually seen language. It has only seen word, like token IDs, kind of like this. So when the model says this, actually, this is what its output is. It has never touched or seen words, but it just is able to model sequences, let's say, of numbers and then embeddings. Embeddings is the next idea here, which is breathing meaning into numbers, into these token IDs. And so when you download, let's say, the GPT model, you would get with it a table of, let's say, vocabulary size and embedding for each word that the model knows or each token that in the model's vocabulary. This is how you can look at it. I don't know if this is up to date with the latest versions, but it was when I was sort of looking at it. So, and you can just pass it, let's say, the token ID. So there's a token ID of the word the, and you can, if you're like me and just you're curious and you want to look at these numbers, do they make sense? They look like this. So we have our words. They're converted into tokens. Through embedding, they're converted into vectors, kind of like the numbers that we saw previously. And these are really the input into the transformer block. And if the input is, let's say, 4 tokens, you'd have these 4 tracks going through the transformer block and an output at each one. And then however many blocks that you have, you can sort of, each block works on the output of the previous one. And these are called hidden states. When you're doing text generation, the one that you predict the next token using this final one. So if we're predicting, let's say, the word redemption, the model would be working off of this final hidden state of the final token. Okay, so how do we turn computation into language? How do we project the output into language? And it looks kind of like this. So where this is the last hidden state of the last token. So the model has processed it, done a lot of crunching, and then it outputs this one vector. Let's say, language model head would project that. So it would give a score to each word in its vocabulary, each token in its vocabulary. And we just pick the highest one, or we can. That's one type of output selection. There are other decoding strategies is the word for this. But say you just pick the highest one, that would be the word redemption. So now you scale it, and that's how you sort of have these massive language models. They process all of these tokens, and then in the end they give you an output, and you feed that autoregressively. So this token that comes out is fed back into the model, and that's how the model continues to produce token after token.
Hey, Jay, I have a question about scaling. So what do you mean by this? Is this scaling like the architecture, or are there other things we should consider when we talk about scaling transformers?
Yes, exactly. So I'm talking about how do you go from, let's say, GPT-2 to GPT-3. So you have larger models, larger training sets. And then even you layer a higher, let's say, number of layers, more transformer blocks.
Great. And then a kind of follow-up question would be, so at Cohere, I think you mentioned you guys are also training large language models yourself.
Yes.
And so I'm kind of wondering, like, what kind of considerations go into curating the data sets when you're doing this? Because we know that GPT-3, for example, has a wide set of kind of known biases and can lead to some kind of generations that maybe are sort of harmful or offensive and so on. And I'm just kind of curious how you guys think about this.
Yes, absolutely. So there's the team works on filtering the data sets for toxicity. I think there's a paper also there that I can share after with the team. So exactly that filtering of the data set is a very important component that leads to models hopefully that can produce better generations.
Awesome. Thank you.
Amazing. Thank you so much.
So was that the end of your talk?
That is the end of my talk.
Oh, great. Cool. Great. So we have a few more questions on the forums. So this one is more of a, say, general question. I'll put it here in the chat. So do you see a future in symbolic learning rather than probabilistic approaches? And I think this is kind of like, the big topic on Twitter between Barry Marcus and, other people who are like connectionists. And I'm curious to see what your thoughts are.
True. Yeah, I don't have sort of much of an opinion. I think we can probably use a little bit of both. The probabilistic has really proven itself. So I don't think you can go without the probabilistic, but can you infuse it with a little bit more rules? Like that's what we see in chatbots, so to speak. You can use some of the probabilistic, but you have to sort of encode some of your rules to actually have something that you can, let's say, ship out to your customers.
Yeah, I think a kind of very related question here is whether like transformers or deep neural networks in general can do true extrapolation, and whether we're just doing interpolation on some sort of manifold in a lower dimension. And I think this is generally what the symbolists are always wanting us to pay attention to. But
True. And there's some work on causal sort of inference that's been sort of dripping more and more into NLP, and that sort of maybe goes beyond just, let's say, correlation into maybe encoding some of the causation.
Cool. So another question we have here is So, your blog, as I mentioned at the start, has kind of helped everyone visually understand what's going on under the hood, and sort of what concept or architecture is like next on your list.
Yeah, so a lot of what I focus on, especially sort of in my work with Cohere, is how do we get the best results from these models in the real world, and how do we apply them to real world problems. So I've been thinking about things like, what are the best ways to explain and think about things like prompt engineering, and what's the best way to sort of fine tune a model. What should the data set sort of look like? So a lot of it I've been sort of thinking about the applied side for a while now, and that sort of gives me some exposure into things like or areas that are interesting, both on generation but also on the embedding side, kind of like dense retrieval and semantic search, and these are sort of very interesting applications of models, both of the BERT and the GPT types.
Awesome. I think we have another question here. It's a bit of a long one. I'll see if I can just read it out. It doesn't quite fit. So it says, let's see. So for T5, there's been around 3 approaches that have been used to fine-tune pre-trained models for all downstream tasks. So this is kind of like where you fine-tune all of the layers, or you just freeze some layers, or do gradual unfreezing. And the question is that for models like BERT, which are more these encoder-based models, which of these approaches do you think is best? Kind of using freezing or just fine-tuning the whole thing?
Yeah, so it's a trade-off. It's really a trade-off. So you can get some value without fine-tuning. You can fit some classifiers on top of the frozen model to begin with. You can freeze some layers and train, let's say, the final layers, and you can fine-tune the entire thing. But the more fine-tuning that you do, the more training that you do, that will take more time. Might need a little bit more data. There isn't a one-size-fits-all. Unfortunately, in machine learning, most of the answers are always depends on the case.
Exactly. And I think this is kind of very closely related to this follow-up question, which is sort of how do we know how much we should fine-tune a pre-trained model? So are there some general heuristics or strategies that you sort of think about when you're doing fine-tuning?
So fine-tuning is a different beast. So it's a word that can use different things. It depends on the complexity of the task that you want the model to accomplish. So if the model has come across your task in its training set, for example, then you don't need a lot of fine-tuning. Because if you, let's say, get data from the web and you train the model to do language modeling on it, it would see things like paragraph and then in summary and then a summary under it. So it wouldn't need a lot of data to grasp the concept of let's say summarization, because it was already sort of kind of trained on it. But if you have something where the relationship between the input that you want and the output is difficult, then you will need a bit more sort of data. And it's similar to however you want to fit features and labels in a general machine learning algorithm. If the relationship is easy, if it's sort of the model is able to do it with less data. If it's complex, then that's you might need infinite data for it.
Exactly. And I think this is also perhaps why everyone has got so excited about models like GPT-3, because they kind of showed, like in Tom's talk, he mentioned this kind of curve where you can see, the performance as a function of number of examples. And in the few shot case where you only need 10 examples and you're still, almost, several tens of points better than everything else, this is quite impressive. And maybe just one last question for you, because at Cohere, I guess you're doing few shot learning, is do you see this technique of prompt engineering or few shot learning becoming kind of as commonplace in industry as the current paradigm we use of collecting several thousand examples and training our classifiers on it?
Yeah, so it is, and it depends on the use case, and it's really better for some use cases rather than others. You can have a lot of, let's say, cases where you don't have that data, or it's very difficult, but that relationship is somehow encoded through examples that the model has seen before. So it's for people without a lot of data sets, few-shot learning is one thing to experiment with. It is convenient, but it has that, it's again, it's empirical and experimental sort of in nature. But if you have only 5 or 10 or 50 examples, it's worth experimenting with it if it's too expensive for you to actually get enough of a data set to train a full model.
Totally. So that's, I think, all the questions we have from the community right now. And thank you once again for this beautiful talk and for taking part in this event. I think everyone really enjoys seeing your amazing slides and images.
Amazing. Thank you so much. I appreciate it. Love all your work. Happy to be here. Thank you so much.
Bye.
Bye.
Thank you, Jay. Have a good one. So we are a little bit of time before our next speaker time to talk because Jay was super insightful and very clear. So I'm going to give you a quick overview of our part 2 of the course while we wait for our next speaker to be fully ready. Let me just share my screen. And we'll get going. So part 1 of the course was teaching you the basics of how to use a transformer model, especially a pre-trained model, and fine-tune it on a text classification task before sharing it with the community using our tools to put it on the Model Hub. And part 2 of the course main goal is to show you how to tackle any NLP tasks. So for this, we started by bit longer dive into the datasets library and the tokenizers library because they are very helpful they have lots of useful tools to tackle some of the most challenging tasks, like for instance, question answering. So the datasets, so chapter 5 goes over the datasets library and shows you how to load the dataset, especially if it isn't from the hub, but you have your own data, which is going to be super useful if you want to tackle your own problem. And then it's showing a little bit how to preprocess that data, so to select a few random samples, how to preprocess it, how to split one data set into a training and validation set. It's showing exactly how datasets work behind the scenes to make sure that you don't go out of RAM if you have a huge dataset, using Apache Arrow behind the scenes to make sure that your dataset is on disk and not really in your RAM. And then it will explain to you to create your own dataset and upload it to the hub. And there is a last section about how to use how to do semantic search and using embeddings with AISS. I'm not sure if I'm supposed to spell it or to say it, Lewis.
Yeah, I never know. And I also should apologize in advance for my Australian accent. So if people are watching all these videos going, what the hell is he saying? Then
So subtitles, you can activate the subtitles on each video and they're pretty good. So. The next chapter is a deeper dive into the tokenizers library to inspect what those tokenizers are backed by. The tokenizers library has tokenizers that are backed by Rust that we call fast tokenizers in the transformers library by opposition to the Python tokenizer, which we qualify as slow. That's because with the Rust library backing those fast tokenizers, we can parallelize the tokenization and go like between 10 and 25 times faster to tokenize lots of text. So this section will explain to you how to train a new tokenizer. For instance, if you have the GPT model in English, but you want to train a GPT model in your own language, so you will need to train a new tokenizer for that, but you want to use the same algorithm as for GPT. So there is one single method to learn, and this chapter tells you all about it, that helps you train your new tokenizer like GPT or like BERT or like T5. Then you have a section about the fast tokenizers' special powers. The first thing is to evaluate why they are faster and how much faster they are compared to the slow tokenizers. And then it goes in depth into the features that we added in the tokenizers library that are very helpful to go back from a token to the span of text that generated it, which is super useful for token classification or question answering. And so that's why it's then we do then a deep dive into inside the token classification pipeline and inside the question answering pipeline to explain exactly what happens between the model predictions and the answer that those pipelines give you. And then we make a deep dive into what happens inside the tokenizer. So the first step are the normalization, which is like cleaning the text, for instance, removing the accents for BERT models, or lowercasing everything if you have a model that is used to that. And then there is pre-tokenization, which is splitting a text into words before the model of the tokenizer is applied, for instance, here to then separate today into 2 separate tokens. And then post-processor applies the special tokens. For instance, for BERT, there is a CLS at the beginning and the SEP at the end. So the first, this section goes over normalization and pre-tokenization, and then you have 3 different algorithms that are supported by the tokenizers library, which are BPE, WordPiece, and Unigram, and they all get their own section to explain to you how they work to tokenize input, how they were trained, and and how you could go to train your own tokenizer using one of those algorithms. And then the last section in this chapter explains to you how to build the tokenizer block by block using the tokenizer library, and then how to use it in the transformers library to tokenize all your text before training or fine-tuning a model with your new tokenizer. Then chapter 7 is really the big chapter of this part 2. So as I said, the goal was to teach you how to tackle any NLP task, and this is the chapter that delivers that. So it begins with token classification, which is a bit like text classification, but you have to predict one label for each token inside your text. Then we go over mass language modeling with fine-tuning a BERT model over the EMDB dataset, and we can see how a model that was used, that was very generic. So this is a great mask. It would predict some generic terms, and then after being fine-tuned on the MDB dataset, it will predict movie or film to fill the sentence because it's been used to a dataset full of movie terms. The next task is translation, how to translate the text into another language. Then there is a whole section about summarization, which is taking a very long text and extracting a very small summary, so like very, very short summary for that section to train the model fast. We decided to train an extreme summarizer of movie reviews. Then there is a section about causal language modeling, which is also going to show you how to train a new model from scratch. And lastly, a section about question answering and how to pre-process and post-process the data to create a model that is capable of finding answer to questions inside a context, like this one, which was able to answer this question from the Transformers README and find the deep learning libraries backing the Transformers library. And then in chapter 8, we did a little bit about how to tackle the most common NLP tasks. How to ask for help when you get a problem. So it begins with what to do when you get an error. And in this chapter, we teach you how to read the Python traceback, which can be very overwhelming at first if you don't know what to look for. But hopefully this will help you analyze your error and help you debug your own training. Then we wrote a small section about how to ask for help on the forums, which is to make sure that you include all the necessary information so that all the members of the community can help you very fast to solve your problem. We then made a section that is more specific about debugging a machine learning training, whether if you're using the trainer API in Pytorch or Keras with TensorFlow. All of those sections both have content with Pytorch or TensorFlow, and you can switch from one to the other with this little button at the very top. And so it's going to explain to you what to look for. So the steps to look for: first debugging your data, then your model, then perhaps a backward pass of the optimizer step. And then we finished this section with how to write a good issue on GitHub to make sure, again, that you include all the necessary information so that the maintainers can help you solve your problem as soon as possible. Or debug and make a fix if necessary in the corresponding libraries. So that's it for a quick overview of that part 2 of the course. We hope you really like it. If you have questions about any of those parts, you can go on the forums. There is a course section that we showed you before, and in this course section there is one topic for each of the chapter that we just created today. So don't hesitate to go there to ask any questions that you have about the course content. And I think we're ready for our next speaker. Lewis, what do you think?
Yeah, maybe we could just, for people who are just joining the stream now, just quickly show how they can ask questions for the next speaker.
Oh, yes. Very good idea. So our next speaker is going to be Margaret Mitchell. I'm going to introduce her in a moment, but you should go on this topic in the course category to ask any questions that you want. And if you find a question that you would really like to be asked, let's go, for instance, in this topic. You can see that there is a little heart beneath each topic. So make sure that you like the question that you want to be really asked, because if we have too many questions and don't have time to ask all of them, we'll select the one that has the most likes. And let me stop sharing my screen. And so, like I said, our next speaker is going to be Margaret Mitchell. Hi, Margaret.
Hi, how are you?
I'm very good. So Margaret is a researcher working on ethical AI, currently focused on the ins and outs of ethics-informed artificial intelligence development in tech. She has published over 50 papers on natural language generation, assistive technology, computer vision, and AI ethics, and holds multiple patents in the areas of conservation, generation, and sentiment classification. And today, she will talk to us about the values in machine learning development. So let me put your screen in the stream, and then we'll let you go on with your talk.
That's good. Everyone can hear me okay? Yeah. Oh, it even says so in this little preview. Cool. And then to see the comments, I can look maybe on the right side of the screen. I would be really happy for people to ask questions as I go. That said, I might get lost in what I'm doing and miss that someone is asking a question. So I'll try my best. Okay, so hello. Thank you for having me. I recently joined Hugging Face to work on things like values in ML development. So I'm going to be here, I guess, a little bit as a wet blanket, but also hopefully providing some useful insights into the development. Okay. So by now, the machine learning development pipeline is relatively familiar to people who work in AI. So first you collect data, then you train and test a model. You can add additional post-processing, such as selecting among a ranked list or applying thresholds, then evaluating, in order for the model to output an eventual decision or answer, and people see the output. But before we even begin the process, the data itself encodes a subset of human perspectives. So what people choose to talk about and how they talk about it based on their experience. So the idea that a data set can be unbiased, which is one of these sort of questions that comes up in the data versus model debates, it's actually both can be biased. And saying that a data set can somehow be unbiased misunderstands what a data set is by definition, right? So a data set is not everything and all experience for all of humanity in the world ever, or in the universe ever, right? By definition, it is a slice of all of that. It's a subset, it's a snapshot. So that means that it is biased with respect to everything else in the universe ever, right? It's a very limited subset, specifically collected from the world, with all kinds of skews reflecting the way that people represent themselves, as well as skews in data collection and annotation, and the way that people talk about the world. So we see biases. We see biases like reporting bias, which is selectively sharing only specific kinds of information. Think about how often people announce that they're breathing, for example, right? All these things are happening all the time. We don't describe them. We don't talk about them. They sort of go without saying. And that means we don't see it in the data, right? So if we're to guess how often people breathe based on a web crawl, we would probably get it wrong. And we also see effects like racism and sexism and ableism and nationalism expressed throughout, which reflects just basic human behavior, right? So these biases then have a ripple effect throughout the rest of model development, as the training data itself is the only information that a supervised machine learning model can learn from. Other kinds of human biases are then layered on top of this and injected into model development by the choice of model, the choice of the objective function, how the model is evaluated. These choices persist in the rest of the model lifecycle. So for example, there's the default effect, which is going with whatever is default for the model you're developing and assuming it is appropriate. So this happens in our model architecture choices. Although, this talk about transformers, these talks about transformers are sort of showing what happens when you move outside of that default effect, which until transformers were largely, sort of recurrent structures. But it's also things like our optimization choices. And then this is even more true in applied product contexts, where it's used in different kinds of contexts. There's a similar effect of anchoring bias, which is sticking with what one is familiar with. So think of what your loss function is, right? We don't tend to think a lot about that unless we're specifically writing a paper on that. Human biases are further injected into any post-processing decisions or a lack of post-processing, right? So just because you don't think about it doesn't mean that something isn't happening. It just means that you are making the choice to have whatever is in there as a bias persist as a bias. And this is also where things like congruence bias comes in, confirmation biases. Both are biases where you tend to pay attention to outcomes that are familiar to you and leave out outcomes that aren't. So that means we need to do additional work in development to think through the ways that the model can affect different people. And this is a place where risk harms analysis is really key. And finally, once a model is deployed, people see the output and begin to act on that output. But it's not the end of the ML lifecycle, right? So as people act on the output in the outlets where the data is collected, so think about content moderation that you see on YouTube, on Facebook, that the recommendation systems you see in so many of the different apps we use, that creates more data as we interact with those systems. And then that becomes training data for an updated model, basically encoding all of these biases essentially permanently, right? So this creates an echo chamber feedback loop where the model then learns from the data that has already encoded the biases in the first model decisions. And so this can amplify problematic decisions over time. I like to refer to this as bias laundering, where the final model can have all kinds of ethical issues, and it can be difficult to pinpoint the exact sources that cause them. Although it can be hard, it is part and parcel of the model. So really important to actually model and factor in. I like to call this bias laundering also because it allows me to use this GIF. It is one of the only GIFs I had made by myself, and I'm very proud of it. I just read that when women make jokes in talks, it reflects poorly on them. So I guess I'm reflecting poorly to everyone. Apologies. Okay, so the input data set defines what we care about for the model. The default approach to development is to simply use the training data that is available in a specific data set and to evaluate on the evaluation data that is available in that data set, right? So if critical aspects of the problem space aren't represented in the pipeline, then deploying the model means you are making the value judgment that these aspects should not be represented. So if the data, the training, the post-processing creates models that disproportionately underperform on some populations, you are implicitly making the value judgment that some populations should receive worse performance, right? So machine learning development isn't value neutral. You can just, for lack of a better word, be ignorant about those values in your development. And what this means is that we have to think critically about values encoded throughout development if our goal is to advance more human-aligned, more ethics-informed kinds of artificial intelligence. So this brings us to the role of ethics in AI and the role of values. So ethics doesn't provide an answer, but rather it provides frameworks for analyzing problems in light of different human values. So some example human values are shown on the right. And these are exactly the values that can be incorporated not only within the development pipeline, but within the development culture more broadly. So having a basic understanding of the major ethical theories will help us in learning how to articulate and justify our decisions. So let's dive a bit more deeply into the ethical theories that can drive the production of AI systems. So broadly speaking, there are 4 main families of ethics. Meta-ethics and descriptive ethics are concerned with analyses of ethics in and of itself. Normative is concerned with the norms, the standards, the criteria that define principles of ethical behavior. These are what provide the tools for ethical analyses and development. And applied ethics are essentially ethical theories realized in practice. And within ethics-informed development in a technology company, this would correspond to something like the organizational ethics or the organization's principles. One of the key ideas here is that we all have different senses of morality. We have different cultures and religions that prioritize different kinds of values. So, for example, respect and honor for family tends to be relatively underrepresented in Western philosophy. But when we're working within an organization, these values need to be defined at the organization level in order to provide a common ground of values that employees can build off of and base different decisions on. So there's often this question of whose ethics, right? Like it's so hard to decide. There has to be one, and it has to be one that we all agree on. But that's not right. The question of whose ethics is simply, it's the organization's ethics. And every organization will be different. You can think of this as a business differentiator or maybe a grad school differentiator, whatever it is. And these ethics, these values can be defined by culling together the values from all different sources, including all the people who have been hired, right? So there is not one good ethics. There's not one way to say this is ethical and this is not. It's all a function of the people there and what the values they prioritize are. All right, I hope that makes sense. So as a vehicle for operationalizing ethics within a larger development pipeline or within an organization, normative ethics in particular provide several different perspectives. So at a high level, these perspectives concern standards of criteria. There are 3 main theories. I'm probably doing a horrible job. I'm not an ethicist by training, but I've very much tried to learn ethics within AI. So these are things like virtue, consequentialism, deontological ethics. And in the context of ethics-informed organizational processes, we're largely following a deontological ethics that has been informed by virtue ethics and consequentialism. So let's turn again to our pipeline, where we earlier highlighted how different problematic behavior can be propagated and amplified in a model. In the collection of data, this first bit, values of concern include copyright, consent, fair pay, diversity, and the right to something like contestation, the right to say that you don't want to be in the data. Currently, the state of the art on all of this is terrible. So generally, copyright is not a large part of what's taken into account during data development. Consent is largely absent, at least the sort of informed consent that we would want for people whose data is being used for training models. Fair pay, often it's no pay, so that sucks. And we generally fail at diversity, in part because the culture around machine learning looks to get annotations as if the production of annotations is some black box where you throw in what you want annotated and you get it back, ignoring that everything that happens in that process brings with it tons of different biases. And what country this is happening in is really going to affect what kinds of annotations you're going to get. Okay. And then in model training, values of concern include how appropriate different decisions are in light of the foreseeable effects of the model. right? So you have to think about how this will be used in context. Will these people know what a decision threshold is and how to change it based on what they want to do? Usually not. And so it's very critical to think through how these models will be applied in practice. And in post-processing, values include the consideration of trade-offs and aiming towards fairness of outcomes. So we can now further examine what these ethical values mean within this first data stage. And I would say defining values in data collection and annotation is one of the most pressing issues in technology currently. Questions of who owns the data, whether it can be deleted, what sort of profit or benefit can be derived from it, all come into play. And I like to call this the data bottleneck because it's a touch point of information flow from human thought to AI, but it's the source of an incredible amount of issues. So in particular, there is not a way to have something like the most values, right? Or the most ethical thing. There are trade-offs and tensions in all decisions. And so it goes back to the organizations or the individuals, maybe if you're working alone, what your defined values are and what your prioritization is among them. So for example, we may want to release a data set to help with benchmarking and reproducibility. But this comes with the trade-offs of lack of informed consent, perpetuating problematic ideas that are there without consent, and the fact that the data can't realistically be deleted yet. We don't yet have a state-of-the-art where we can remove data. This means details of individuals in the data can not only be shared, but continually amplified and proliferated without their consent, right? There's this sort of misunderstanding that, well, if it's out there, it's already public, so we can use it. The problem is one instance being public and sort of generally difficult to access is different than being spread all over the world to hundreds and thousands of people. These two things are not the same. And so, you know, in the effort to have benchmarking and reproducibility, we're often making the choice to amplify and proliferate problematic content without consent. We may also want to aim for things like inclusion and diversity within our data, representing different people with respect to their different norms. But this comes up against things like exploitation, and tokenism and stereotyping. That's when data is collected with a specific goal of diversity by ignoring sort of all the other factors at play. It's not yet clear what the best methods are, but there's still a lot of work to be done in at least doing somewhat better. So I'll give you an example. A couple of years ago, Google was working on face verification phone unlock for the Pixel and hired a vendor because they needed more photos of Black people. So what did the vendors do? They went to a homeless camp in Atlanta and paid people there who were Black $5 for their face to build Google's diverse facial recognition system that, you know, obviously they would make a lot of profit from. So a few issues there. One is equating Black people with homeless people. So that's some sort of disgusting stereotype I don't think I was even aware of, but there you go. Exploiting people, obviously, $5 and without very informed consent. And also tokenism, where you're not looking at how to include this person in light of what their general life is like, their culture, everything else like this, but actually just focusing on who you could quickly get because of this single characteristic. That's tokenism. Right. So one of the key solutions to operationalizing ethical data development means defining values and priorities upfront and constructing data specifically based on the values. So this massively expands what it means to collect and work with data, making data collection itself a detailed and nuanced process with dedicated roles to handle different aspects of data development and corresponding artifacts that allow the values encoded in data selection to be further examined throughout the pipeline and then within final release decisions. So this can be seen as a life cycle for the data as a whole, as it requires continual monitoring and analyses of the effects of the data and updates then based on these analyses. Now we can turn to the details of operational.
If I can just interrupt you 1 second. We have a question that's very relevant on the data, which is, how do we push for adaptation of more ethical data sets, not ImageNet, CC4 Lion, for example, in major conferences?
Yeah. So maybe not obviously. So a lot of researchers have increasingly been paying attention, and a subset of researchers have been publishing papers on this. So Abeba Berhane has done incredible work on this. Jesse Dodge has led some amazing work on this for C4, right? So the fact that these papers are starting to get accepted is a massive step forward in sort of this general understanding. They were largely rejected, 2 years ago. So there's been an increase already in understanding why these things are important, in part because of, the small subset of researchers really crying out for it over and over again, and making it clear via not only papers, but Twitter and blog posts and interviews. And, so this is sort of happening now. The key now is to make sure that reviewing rubric actually cares about this stuff. So when you're reading a paper that talks about model training and model evaluation, you have to know critical aspects of what that data set for training is, what that data set for evaluation is. And if it's too much to include in the paper, you can have it in the appendix, whatever it is. But while we continue to, really celebrate papers that don't discuss the data they're using at all, we're not going to be incentivizing ethical data practices. So reviewing rubric, also awards. I have this idea that you can get an award at a conference for like best evaluation or like best analysis of input data or something like that. Currently, we have best paper awards, which is pretty underspecified and tends to bias in certain ways. But once we can start breaking this down into what we really want, both in terms of reviewing rubric and awards, then I think we can really get somewhere. Yeah.
Thanks a lot. That makes sense.
Cool. I didn't see the question, so I guess I'm not like in the right chat or whatever, but cool. So the next bit here in this model sort of pipeline is the model training. And that's where values come into play around the appropriateness of the loss function and the model. Okay. So I'm going to talk about this via a case study. I was able to work on coronavirus forecasting, which was, amazing to be able to work on. And we quickly found that there were a mass amount of model-based decisions that could drastically affect people when the model was deployed. So if you're not technical, bear with me. I'm going to try and explain. If you are, this might be just a repeat, but this is very important. So false positives in a coronavirus forecasting model means that hospitals might be over-equipped, expecting a need for more beds and ventilators. But a false negative means that there would be less resources than needed, which could end in death, right? So there are trade-offs in different kinds of errors, but arguably a model that tends towards false positives is preferable to a model that tends towards false negatives. And one of the issues at play is the choice of loss function. So if you take a look at the different kinds of objectives that can be used, which are on the bottom left, they treat positive and negative instances the same way. These are all measured in terms of absolute values, right? And so that means false positive, false negative, these basic ideas are treated as equivalent. And so for the value aligned goals of the model, this suggests that some additional work may be necessary for the selection of the most suitable model. Perhaps unsurprisingly, trying to bring this forward at Google mostly meant hostility, and it was a terrible experience. Now I'm telling all of you, still important, even if people are mean. Okay, So moving on, we come to the post-processing and final evaluation. And so here too, it's critical to think through different types of outputs and errors in order to select the most suitable metrics to measure model performance. And it's in this stage that concepts like fairness, diversity, and inclusion are really important. Some of these are more developed than others, so let's talk about them a bit. So for those of you who are not deeply familiar with fairness, one of the most basic ways to think about fairness is in terms of a confusion matrix. So what we have here are a 2 by 2 of references, the ground truth, the thing that's actually there, and model predictions, the thing that the model is guessing. When something exists and it's predicted, that's a true positive. When something doesn't exist and it's not predicted, that's a true negative. The error types we really care about when we're talking about fairness are false positives and false negatives. So these falses, right? So if it doesn't exist, but it is predicted, that's a false positive. If it exists and it's not predicted, that's a false negative. But in one case, a false negative may be better than a false positive. And in another case, a false positive might be better than a false negative. So it's very critical to define what kind of fairness you care about as the equality of essentially false negatives across different groups, equality of essentially false positives across different groups. When you have these equalities based on these kinds of errors, this is what we mean when we talk about fairness. So a case where false positives would be better than false negatives is something like privacy in images. So a false positive here, something gets blurred that shouldn't be blurred. That's just sort of usually a bummer. But a false negative could be something that needs to be blurred, not getting blurred. So that's like identity theft. So we clearly have a decision to make in our model development which kind of errors we want to focus on. And by thinking through in context, it's clear that in a situation like this, we want to make sure to minimize false negatives. False negatives can be better than false positives in something like spam filtering. So here in email, that spam is not caught, so you just see it in your inbox. Usually that's just a bit annoying. A false positive email flagged as spam is removed from your inbox. So if it's from a friend or a loved one, or it's a job opportunity, that's a loss, right? But note that the usage in context really, really matters here. So if foreseeable users include those that are easily scammed, leading to a loss of wealth, then false negatives have a greater risk. And model development needs to balance these different populations in determining the optimal models. The current state of the art, nothing. So low-hanging fruit, we can do a lot better. Okay, cool. So finally, people see the output in this process, and it begins again as people interact with this output, and then the biases are further encoded and more deeply ingrained in the model. I'm not sure how I am on time because I started a little early. I can go.
You have time if you...
Yeah, so I want to have time for questions.
I have questions right now if you want. I can ask. I have a few questions right now.
Yeah. What I'll do is I'll just kind of like wrap this up really quickly, and then we can go to questions.
Perfect. Yeah,
so here's some basic steps forward. And this is sort of what I would like you guys to remember if you take anything from this talk. We need to align considerations of our own values to this larger group that we're working in, these stated values. Thinking through if the technology should exist at all by using this sort of analysis of foreseeable harms and risks by the expected populations, by the people who will be affected by the model, and how it will be used in context. Establishing basic organizational values can be informed by things like virtue ethics, consequentialism, deontological ethics, where things like privacy, fairness, justice, consent, all these things come into play and then can inform, what we prioritize as we develop. Once we start establishing these things as intentional processes throughout the pipeline, requiring artifacts and documentation, we can start to be able to foresee even more potentially problematic outcomes and make more informed decisions on releases. This goes to the question earlier. One of the critical ways to make this move forward is incentivizing ethics-informed development. So this is things like what gets put in review rubric, what kind of awards we get, what sorts of things are rewarded when they're talked about. And one method I've worked on to capture much of this is model cards. A large part of why I joined Hugging Face is because they were trying to come up with ways to scale model cards, and I thought I could help. But it's essentially an artifact to report sort of all of the above. And finally, throughout, the critical, most serious thing that you can do is encourage and reward foresight, thinking through the outcomes with different people in different contexts. And here's what's important to know. Some people are good at this and some people are bad at this. So if you're bad at this, don't say we can't develop AI with foresight. Just accept that maybe some people have a strength in this and you don't, right? I've been corrected that instead of foresight, what's more important is rapid hindsight. No, some people are good at foresight. Let them stop you from having the need for rapid hindsight, right? So this requires placing people in the appropriate roles to make this aspect of development really shine. Okay, thank you. I'm done. I appreciate it.
Thanks a lot for your talk, Meg. It was very insightful. So I have a few questions that were asked on the forum. Let me pick the first one. So how do we protect ourselves against machine learning system designed primarily without ethics in mind? Because we are obviously algorithm being run out in the world right now. And yeah.
Yeah, I mean, this is a really hard thing to answer. I previously thought that part of the solution was to make sure that the development that has already taken place is retrofitted as much as possible. So taking a look at the kinds of evaluation data sets that were used, the kinds of training data sets that were used, doing more further analysis into what errors it makes, and then essentially fine-tuning, updating the model based on that. Unfortunately, I think in part because of this issue where a lot of people in ML are just not that great at foresight and don't really see the point of it, we're going to need regulation. So that's sort of what I think it comes down to at this point. Yeah. Makes sense.
Another question that was a bit too long, so I'm going to read the last part from the forum. So model transparency seems to be a precondition of the mentioned ethical goals. Dr. Mitchell seems to emphasize the role of input data. Isn't the model's way of decision-making equally important, feature importance, etc., for ethical AI?
Equally important. I would say all of the above is important. I'm not sure how to extract that to numerical values to say that it's equality. But one of the reasons why I do have a focus on transparency is because it's incentivization of good practices throughout, right? So if you have to report how your model does with all these errors, then you're probably not going to release it unless it does well. So as soon as you have transparency, this is a way to essentially incentivize good practices throughout. Input data, I do have a focus on in particular because it's what the model knows. It's the model's knowledge source. So there's so much that can be said about evaluation and all these other things, but the issues very much start with what's in the data. So I would say that's a highest priority. Yeah.
And then speaking of data, what about retraining models that are already trained on unethical data? Is it possible to fix them somehow?
Yeah. So, I mean, by unethical data, I'm taking that to mean, data that has a lack of consent, data that our licenses and copyrights are not being paid attention to, data with PII. So I'll assume that's what you mean by unethical data. I do think it makes a lot of sense to retrain and fine tune. And actually, some of the work that I've done has been specifically on bias mitigation techniques and identification of stereotypes and things like this.
Mm-hmm.
Whether it's sort of ethical to retrain, I guess that's better than not retraining if it's going to be deployed. So I guess it depends on the context that you're in. If you're writing a thesis, maybe this will become your topic of how to start from scratch. If you're in an organization and you're retrofitting, maybe the best way is to retrain or fine tune a bit. So I think it depends a little bit on context. Yeah, I guess that's the sort of most relevant answer I have to that.
Okay, there are lots of questions about debiasing. Like I have another one here. While training the pre-trained model, is it possible to add a step including debiasing algorithm? There are emerging algorithms today. Could this make some interesting bias disappear?
Yeah. So there's a lot of work to be done in data that has tended to be not incentivized. There's also a lot of work to be done in models, and this has been more incentivized. And so I just want to make clear, I guess, that one of the cool tricks is around sort of multitask learning. So bias mitigation techniques that tend to work, reasonably well have to do with predicting a few things at once and then discouraging one thing while encouraging another. So, for example, say that you're trying to predict whether or not someone should get promoted. At the same time, you can predict gender. And if you find that the promotion decision is predictable via the gender, then you know that you have a bias system that's biased for gender. Mm-hmm. So one of the adversarial mitigation techniques that's pretty fun, and there's a couple of papers on this. I wrote one, Alex Butel led a really cool paper on this, is you essentially invert the gradient. So you predict both, and for everything it's learning about gender, you say the opposite of that. You essentially multiply by -1 and back propagate, right? So that says, like, you don't know what gender is, and you just tell the model until it's essentially random. And that's really a cool way of sort of removing a gender bias. There's other things you can do with like pairing, but a lot of the key techniques are around just this, like having two or more things that you're modeling at once and encouraging one while discouraging another.
That's a very cool technique indeed. Another question, let me scroll a little bit. There might not be a magical solution, but what's the easiest way to determine whether a text generation model is not racist or sexist? And how do we solve this quickly without losing too much of training data?
Solving it quickly, huh? Well,
yeah, that's...
Yeah, I mean, obviously, as quickly as possible is good if there's sexist and racist things in the world. So, fair enough. So I think that I don't know that it'll ever be possible to have a model that's not sexist or not racist, because I don't know that it's ever possible to have a person who's not sexist or racist, right? I mean, these are all sort of based on heuristics and how our brains work as we're brought up. And so part of, going through like ally training and, these kinds of things means that you have to recognize it and proactively address the kind of patterns that you tend to do. So you would imagine that similarly for a model, you would put in place normative constraints like you do with people. So that means saying that, we are going to mask gender. So there's no distinction between gender when we're training our toxicity model. And so when we have an input gender, we have no way of we don't know what it is, right? And so we won't correlate the two. And toxicity actually particularly has a bias towards the term gay and LGBTQ terms. So there are things you can do like masking those or adding more data. Anywho, the point here is that we can put in place specific normative constraints based on our social knowledge. So this is where social scientists come in, sociologists come in, on how racism and sexism and things like this are expressed. So we can do that, and that's definitely like a quick fix. But a full-on fix might not be possible. But yeah, do as much as you can, definitely.
Another question around the bias in data is how could we balance the filtering of bias between freedom of speech and offensive biased consent?
Oh, that's such a good question. Yeah, I've been struggling with this because ideally we can ground AI development in like fundamental rights or human rights. But if you are American centric, then freedom of speech is like, you consider that like a fundamental right, right? But like in other places, privacy is nice, or like you can imagine freedom from discrimination as to be a cool thing, or perhaps a basic right that people should have. But that comes in conflict with the free speech thing. So I mean, I think part of the issue here is that when you say free speech, there tends to be an assumption that there is some sort of uniform sampling over all data instances so that free speech as a whole is reflected. So you have like people talking about women positively and people talking about women negatively. And so it's all free speech. We want it all. But what in fact happens is that the data sets tend to be heavily biased towards men and using sources where there's misogyny, so like Reddit. And that is not counteracted by free speech about women being awesome or whatever. So yeah, I mean, like one of the things about free speech that is kind of fun to do is actually data collection. So I was part of a project called Project Respect that went to like gay pride parades and had people say like really proud things about their identity and their LGBTQ like associations and stuff like that. And that created like tons of data that we can use in training a toxicity model. That's a lot of work, and you have to have willing participants and hopefully compensate them whatever they should be paid. But yeah, I mean, there's a few things you can do, but keep in mind that the free speech idea is a little bit hampered by the fact that the free speech that we collect is biased and tends to be more misogynistic and racist than maybe a larger sample would have.
Yeah, definitely. And around like the compensating participant for creating the data, I have another question, which is making it mandatory and forcing to create data sets where each participant is highly paid going to put a lot of pressure on researchers from low resource institutions and researchers from low resources countries? Yeah,
that's a really good question. I think this is where things like governments start to play a role. And I think it's also kind of important to note that this also is very destructive to private companies that are that have a lot of money. So it's sort of like, I sort of feel like the larger the organization, the more this will hurt them, right? So if for example, you require Google to pay everyone for the data they're producing, Google's business model would be basically destroyed. So, in some ways, we might think of methods where different compensation tiers, make sense for different kinds of organizations. You could get this via regulation. So, if you're a grad student paying, a minimum wage or whatever for your annotations, that's pretty reasonable. That's pretty normal. If you're, a multi-billion-dollar corporation, perhaps paying a lot more is worthwhile, especially because like you're making profit off of this. So it should be a percentage of that profit in some way. So I think there are ways not to over disadvantage low resource groups or organizations. And I think that it could go the other way, like very much harming larger private companies.
And one last question, which is a bit more personal, is what does the regular day-to-day work look like for you?
Oh, well, so I just joined Hugging Face full-time on November 1st. And before that, I was doing like a lot of contracting and consulting. And so I've just been sort of all over the place. I'm someone who wears many hats. Like I like talking about philosophy, and then I like talking about statistics, and then I like coding, and then I like writing. And so I really don't think I have a traditional day. I will say that I hate waking up before 9 a.m. Pacific time. And so presenting at 9:30 was a feat. I hope I seemed coherent. I think that's basically the only standard throughout my day. The only common thing is that I try and not get up until 9. But other than that, yeah, I jump around between coding and thinking through math stuff and writing papers and reading papers and sometimes answering email. Sometimes. Yeah.
Sometimes. Well, thanks a lot for your time this morning, because this was a super interesting talk and very insightful answers to all the questions.
Awesome. Thank you, guys.
And I'll let Lewis introduce our next speaker while I say bye to Margaret Mitchell.
Sure. So I'll just add Chen and Matthew. Hey, guys. How you going? I think, Chen, you're on mute.
Hi.
Hey.
I'm good.
So this is Matthew and Chen. They're from the Keras team. And Matthew's a machine learning engineer who focuses on high-level modeling APIs. And he studied computer graphics during undergrad and has a master's from Stanford. And Chen is a software engineer from the Keras team who also focuses on these high-level modeling APIs and also has a master's in electrical engineering from Stanford and is really interested in simplifying code implementations of ML tasks. So we're really excited to have you here to sort of help people understand kind of what Keras is, maybe convert all the Pytorch diehards. And before getting started, I just want to show people just quickly how they can ask questions. So if you go to the Hugging Face forums, you can click on the course category, and then you can scroll down to where we have Matthew Watson and Chen Qian. And here you can just post your questions and we'll be voting on them based on likes. And
also the forums contain the links to the collab notebooks that Matt and Chen are going to use.
Cool. So with that, I think, Matt, you're first, right?
Yeah, I'll be first.
So we'll add your screen and we'll see you soon.
Okay, great. Let me actually start the presentation. Okay, cool. Yeah, thanks for joining. I'm Matt and I'm speaking with Chen. We're both on the Keras team inside of TensorFlow. Today we're going to be talking to you about NLP workflows inside of the Keras library. So quick, just kind of plan for the day. I'm going to do the first part of this talk, and I'm going to be just talking about kind of building like very basic models, very basic NLP models inside of Keras and showing what that looks like. Then I'll hand it over to Chen, who's going to talk about kind of like pre-training and fine-tuning using Hugging Face and Keras. Hopefully all of that will take about half an hour, and then we'll have questions. Cool. So before I even dive into my side of the talk, I wanted to do 2 slides, like super quickly, just giving an introduction to Keras to anyone who hasn't seen this before. First off, what is Keras? It is a deep learning API, and the kind of one-sentence version of it is deep learning for humans. But what that means in terms of how we're trying to build our library is really centering it around like simple APIs that kind of reduce cognitive load as you're building up your models. So you can focus on building your models and really trying to focus on kind of a minimal number of actions that you need to take for common use cases. So basically you can get the Keras library and spin up a lot of examples very quickly, start to kind of explore your problem space very quickly. That's a key goal with the Keras libraries. And then another way you can think about it is Keras is the high-level modeling and training APIs that will come prepackaged with TensorFlow. That's Keras. And then I wanted to also introduce just 2 kind of basic abstractions that you'll run into over and over again with the Keras library, and that's layers and models. You might have seen something familiar to this somewhere, but basically you can think of layers as kind of these Lego blocks of like common motifs that you'll see in many machine learning model architectures. And with Keras, you can take these Lego blocks, you can combine them in a whole lot of expressive ways, and then snap them together, and a model will be this collection of layers that kind of map from your inputs to outputs, and the model is going to be the thing that you can like train, that you can save, that has all these high level APIs available on it. Okay, So that was a super, super quick introduction to Keras, the library as a whole. Now I'm going to do my side of the talk that's on these kind of basic NLP models we can build with Keras. And I'm going to be doing this with the sentiment analysis dataset from IMDb. If you haven't seen this, I think it's like 25,000 reviews in the training dataset that are just movie reviews, like 3 or so paragraphs of text describing a movie. And we're just trying to build a model that will predict, is this a positive review or a negative review? And my goal in showing all this is going to first be to just kind of show some basic building blocks for Keras. I'm working with text in Keras. And then the main kind of the thesis of my side of the talk is going to be about this triangle on the right-hand side here, which is that using Keras, you can hopefully go very quickly from an idea to an experiment to seeing some results, and use that to inform kind of the next experiment you run in a nice tight loop. So we'll actually build up like 4 very quick models on my side of the talk. Okay, so we're going to be writing this all in code. So let's start by downloading our data set. Yeah, you can see what we're doing here is we're first just downloading a bunch of plain text files in a couple directories, and then we're going to use a Keras utility to load them as a TensorFlow data set. And yeah, we're batching things, and when data is flowing through TensorFlow, you're going to be seeing everything going through as tensors. That's kind of how TensorFlow works. I mean, you can see once we've loaded our data set and batched it, we have these batches of size 32, where every input, we have just a single input feature coming in for each of our examples, which is a string. I've truncated it here because they'd be too long to show reasonably on a slide, but think each string is, many paragraphs of text, and then each label is a 1 or a 0. And a 1 here means this was a positive review, a 0 means it was a negative review. Okay, so we've downloaded our data set. You kind of immediately hit this roadblock that you'll hit every time in NLP, which is how do we represent our data? You're not going to feed strings directly into any neural network architecture, so you need some sort of transformation of your input before you can even really start worrying about your model architecture. And one approach that you can use inside the Keras library for this is the text vectorization layer, which we'll see in code in a second. But yeah, it's one of our Lego blocks that's kind of just centered specifically around working with text input. So it'll do a few different steps. They're all configurable, but by default, it'll have a normalization stage where you'll remove punctuation in lowercase, a splitting stage, and I think the default option will just split on white space, so splitting into different words. And then there's a number of different ways you can map from that idea of string tokens to some sort of numeric inputs for your model. And the simple model, the first thing that we're going to build, you may have seen this before, but it's called a unigram model. You'll also see this called a bag of words model. And yeah, it's a nice simple thing we can build to start trying to guess if our reviews are positive or negative, where we're essentially just going to look at what words are present in a review and what words are not present in a review. So we're going to build up this vocabulary of the most common words in all our reviews first. And then when we get around to kind of encoding each individual review, we're going to encode each individual review as this big long array of zeros and ones that kind of aligns with our vocabulary that we've learned. And if you get a 1, that means that word was present in your bag. So the word movie is present in this review, we get a 1 at that movie index. Good is not present, we get a 0. So that's the rough idea for the model that we're going to build. Let's look at this in code. Yeah, this is actually a complete training example for this unigram model, but I'll try to break this down step by step. So first off, like kind of the overall flow that we're doing here is we're going to define this kind of symbolic input at the top, which is saying that we have, our inputs are a single feature. It's a single element string that's going to be coming through. Then we're going to transform our inputs with some layers. It's 2 of these Lego blocks that we're going to snap together. To transform our inputs to outputs. We build a model over our inputs and outputs, and then we train that model. So that's the rough flow, and then we can step through these 2 kind of blocks here. The first thing here is probably the most dense, which is the pre-processing. And this is where we're going to use that text vectorization layer we talked about. So first thing we're doing here, because for a second, we're just going to be working with our features and not our labels, is we're going to map over our data set. We're going to toss out the label just to give us the plain reviews alone in a data set. Then we're going to build our first Keras layer. And you can see when you're building a Keras layer, you normally will initialize these with some amount of configuration as to how they're supposed to work. So this output mode multi-hot is where we're asking for this bag of words encoding of our input. And then this max tokens 10,000 is just saying how big do we want our vocabulary to be. And we're saying we want to learn the 10,000 most frequent words in all of our reviews. And the way we actually learn the 10,000 most frequent words, you could actually supply a vocabulary yourself if you knew that and you had trained it yourself. But you can also use this utility function that we have called adapt, which is actually going to loop over all of our features, all of our input reviews, and just learn the 10,000 most common words that we see in all reviews. So when we've learned our vocabulary, we're ready to actually call the text vectorization layer on our inputs. Keras layers, when you want to call them, you can just treat them as functions and call them on your input. And that will give us this bag of words representation that we just talked about. So from there, then we actually still need to build a trainable model on top of this. And the simplest thing we can think of to do there is kind of just add a linear layer on top of this, and we'll just call it a day there. So we're gonna, we're mapping each of our inputs to this 10,000 long array of ones and zeros, and we're just gonna learn a linear combination of all of those 10,000 values, pass that through a sigmoid function, and that's our whole model. So yeah, just logistic regression on top of our bag of words. So once we've done that, we can define our model. Compile is a Keras function on models for just kind of setting up how your training is going to work. So we can specify our loss function here. We can say we want to track accuracy here. And then we just train for 5 epochs. So yeah, that's a complete code example in Keras. I encourage you to try this out in a collab if you would like. But yeah, essentially now we've built our first model, and we've kind of made 2 design choices here. We've made a design choice around how we want to represent our input data as some sort of numeric input, and then how do we want the actual trainable architecture of our model to look. And now that we've built up our first example, we're just going to iterate on a few different ideas for how we can build up our model for the rest of my part of the talk. So take 1 was what we just did, unigram model. We're taking in our input reviews, we're mapping it to a bag of words where we're throwing out all of our sequence data, we're throwing out everything except just what words were present, what words were not present. We don't even care how many times the word film appears, we just want to know is it in the review or not. So this is the exact code I showed you before. I've just kind of zoomed in on the actual meat of the model here because we're going to just be iterating on this for the rest of the talk. But what does this look like when you actually run it? How does it perform? First thing you can notice here is that it's a very small model that we're actually training. It's just 10,000 parameters because we're just learning a weight term for each term in our vocabulary, and that's it. That's the whole model. And we're actually already doing pretty well. We've got 89% validation accuracy on a holdout data set. So yeah, that was take 1. And now we can start doing what hopefully Keras is going to make it easy to do, which is iterate on a bunch of different ideas, kind of explore the landscape of this little problem that we're working on. So take 2 we can try is a bigram model. And bigrams are just fancy word for a pair of words together. So if you're looking at this first sentence, this film is a bigram in this sentence, a travesty is a bigram in this sentence. And we want to build the exact same sort of bag of words idea, but we now also want to look at bigrams in addition to unigrams. And you could think how this might be useful already, because not good, the bigram not good, means something very different than the unigram good. So by adding in that little bit more knowledge of our kind of sequence data coming in, maybe we can build a more expressive model. So what does this look like in code? We actually have to just make very, very small changes to our text vectorization layer. This is the pre-processing side of our model definition. And we're just going to make 2 changes here. We're going to just bump our vocabulary size. We've changed from looking at only words to looking at words and pairs of words. So kind of our vocabulary space is a lot bigger. So we want to learn a bigger vocabulary inside of that space. And then this ngrams2 argument is just where we ask the text vectorization layer to also look at bigrams as well as unigrams. Everything else stays exactly the same. We keep learning our logistic regression on top, and that is our entire model. So if you ran this in code, you would see, okay, we bumped the vocabulary size from 10,000 to 20,000 parameters, just doubled our vocabulary size, so we've doubled our model size, but we've actually bumped our accuracy. So now we're over 90% accurate predicting whether a review is positive or negative. So that's great. It was a nice, quick, and successful experiment that we ran. And yeah, now we'll try 2 more models on this side of the talk. And the first thing what we'll do for the next 2 models that we build is we'll switch from, we'll say, forget the bag. We're not going to do the bag of words model anymore. And we're going to do this very common thing in NLP, which is we're just going to map each word to an integer index. So we're keeping our sequence data in our pre-processing, and we have this movie was bad, this list coming in. We're going to map each individual word to an index. So this is the 4th index in our vocabulary. So this maps to a 4. Movie is the 1st index. It maps to a 1. And this output is going to kind of be our pre-processed inputs that we're working with for our last 2 examples here. Okay, so what can you do with integer indices for words? The common thing you'll do in most models is embed them. So we're going to take our input sequence, we're going to take our input string, we're going to map it to a sequence of integers, and then we're going to map each individual integer to a set of trainable parameters. So the index 11 will map to, in this example, 4 trainable parameters, same with 20. I'm going to learn this big, long kind of horizontal embedding that you can think of, where we're just pulling out individual columns for each word. And hopefully that learns like this rich but low dimensional space for all the words that we have coming in. And then, because we're just trying to keep our models simple on this side of the talk, we're going to do the simplest thing we can think of with our sequence of embedded words, which is just average them together, not even try to do anything fancier than that. Okay, so let's dig into this in code. We still have our pre-processing block and the part where we apply our actual trainable layers. The pre-processing block is going to change a little bit here. We're switching our output mode. So this is where we're saying we don't want our bagged model. We actually do want a sequence of integers coming out of our text vectorization layer. Our vocabulary size will move to 10,000, and then output sequence length. This is just something to keep this example simple, where we're going to say for every input review, if it's less than 250 words, we're just going to pad this with zeros till it becomes 250 words. And if we get a review that's longer than 250 words, we're just going to chop it off at 250 words. And that'll just keep training simple here. And then for the actual trainable model, we have a good bit of new stuff here. We're using our embedding. So this is where we take each word and map it to an embedding for each word. Rather than 4, like on the slide I was showing, we're actually mapping to 32 different trainable parameters for each word. We apply some dropout, and this is just because we're building a much more expressive model with a lot more parameters here. So it helps to bring in some dropout just to avoid overfitting. And then we're doing this very simple, the global average pooling 1D is really all it's doing. It's taking everything in your sequences, in your input data, and averaging them together. So we'll build that model. We'll still build a logistic regression on top just to map everything to one single prediction. And that's our whole model. So if you were to run this, you'd see we've kind of exploded our parameter space a bunch because our embedding is now, it's pretty big. We have 320,000 parameters compared to 20,000 for our simple bigram model that we were looking at last time. And we've actually not improved our validation accuracy at all. We've gone from 90% with the bigram model to 87%. So maybe not the best line of inquiry to keep going down further, but at least this was a quick experiment we could run, try out, and see how it works. Okay, and then the last kind of model that we're going to build here is a recurrent one. And probably a lot of people in this talk have seen this before. I won't go too deep into the details of how a recurrent neural network works or anything, but the idea is we're going to build this LSTM model, do the exact same transformations as we were doing before, where we take our input sequence, we map it to a sequence of integers for each word maps to an integer. We map each integer then to an embedding for each word, which is hopefully this this low dimensional but rich representation of each word. And then we feed all of those into this recurrent neural network, which is going to be a trainable bunch of cells where we process each word one at a time. And as we're processing the word, our trainable cell will have some sort of memory of what it's seen before. So hopefully the LSTM can learn some interesting things about our sequences coming in and start to remember what words it's seen before a particular word that it's looking at in the sequence. So that's the idea. What does this look like in terms of code? We'll keep our input representation exactly the same. We keep our preprocessing the same. We keep our embedding the same. Dropout, everything's the same, except we're just going to switch out our pooling layer with a trainable LSTM layer, and that will be it. So if you ran this is our most expressive model. Yeah, we started with a 10K parameter model, and now we're at 336 parameters. And we're actually doing the worst of all of them with our biggest model. So we top out at about 86% validation accuracy, and you can see we're already really struggling with overfitting. Okay, so that was a just very quick introduction to what it looks like to build 4 different simple NLP models with Keras. And again, the rough idea and what we're trying to do with the library is to make it really easy to run kind of experiments like this, to come up with some idea for either how you represent your input text, but when you feed it into your model, how you preprocess it, or an idea for how you want to actually architect your model itself and go very quickly from that idea to some sort of results. So yeah, that's entirely what we're aiming to do with the Keras API. And you can already see how it's given us some useful information into our problem here, where we've found this nice sweet spot. The n-gram models actually turn out to be when you're not doing pre-training, and there could be a lot of reasons you don't want to do pre-training in a problem like this, where we built a model with only 20,000 parameters that is going to be incredibly computationally efficient. It'll give you really fast inference times, and it's already greater than 90% accuracy. So you can play with this more. Certainly, you can get to even better accuracy with n-gram models, but we've already kind of found this nice kind of sweet spot to go dig into. And you could try this, you could try more things, attention mechanisms, whatnot. But yeah, that was just a quick intro to trying a few different simple architectures in Keras. But yeah, if you did want to get to like state-of-the-art performance, you'll want to do pre-training and fine-tuning. So for that, I will hand off to Chen.
Awesome. Thanks a lot, Matt. I'll add Chen to the stream. Would you like us to do questions for your section altogether at the end?
I think we're going to just do questions at the end, if that works.
Yeah, I'll do together.
Perfect.
Okay. Thanks.
Great.
I'm going to go present here.
So I'm just going to add Chen's slides. Great. So sounds good. So take it away. Thanks.
Oh, cool. Hi, my name is Chen. In the second half of the talk, I would like to demonstrate with real code examples on how to do fine training with Hugging Face and Keras. The main takeaway we hope you'll get from this talk is you will find it simple to do fine training with Keras and Hugging Face. We will use the same task as the first half, the IMDb sentiment analysis in the second part. And some background. For people not familiar with fine training, the idea is starting halfway towards our target. Instead of building a model from scratch, it's pretty similar to buying a house. Imagine you want to buy a house. Usually we do not buy an empty land and build a new house, but we buy a house and do the remodeling. The remodeling process is pretty similar to fine training idea. And in our IMDb sentiment analysis task, we can load a pre-trained BERT model and build our model on top of it. And what is BERT? BERT stands for bidirectional encoder representations from transformers. It was published by Google in 2018 and has gained great popularity in NLP community due to its strong performance. Explanation on BERT is beyond the scope of this talk. The main thing we need to know is BERT is very good at extracting representations from texts, or say BERT is a good text encoder. Now let's take an overview at the model architecture we are going to build. First of all, we have the text loaded from IMDb datasets, the movie reviews. And we add a special token in front of each movie named CLS. We will come to the purpose of this token very soon.
The first layer we have is a BERT tokenizer. As we mentioned in the first half, neural networks cannot understand string input. So we need to map this sequence of text into a sequence of integers. It's a job of this BERT tokenizer. The second layer is a BERT encoder. It takes in the sequence of integers and map it into a sequence of vectors. And here we only take the first vector, the vector for the CLS token, to represent the whole sentence. This is a common NLP practice. Basically, if we set up the model properly, the information of the sentence is going to be fused into the first token. Now we have the vector representation. We add a third layer, the fully connected layer, to map the vector into another space, which is usually of a smaller dimension. We call that projected representation. This is going to be our final representation for the input text. And the last layer is straightforward. We input this projected representation into a softmax classifier. The output would be the probability of this movie review being positive and being negative. That's all for the model. Before we look into the code, I want to pause here for a few seconds. I want you to think about one question. Like, how complex do you think make the model work is like? Like, how many lines of code do you expect to write? Or like, how many hours do you expect to spend here? I want to pause here for like 10 seconds and let you think about it. Just give it a guess. Okay, cool. Now with the answer in your mind, let's look at the code. We have in total 5 steps. The first step is to load the tokenizer and pre-train BERT from Hugging Face library, as highlighted in the red box. If you haven't installed the transformer library, you need to copy install to install that, and you pick up the model you want to use. And in our case, we pick up the distill BERT tokenizer fast and distill BERT model. And if you are not familiar with the input and output format of the model, you can play around with it. This is one sample output. And the second step is to load IMDb dataset into a memory. This part is pretty similar to the first half, so I will not jump into the details of it, but I want to pause here for a few seconds to let you look at the code. Cool. Let's go to step 3. Step 3 is to tokenize the data set, as highlighted in the red box. As we already have the data and the tokenizer, we can simply input the data into the tokenizer. The output, like train encodings, validation encodings, will be the sequence of integers we described previously. And we do one more conversion. We convert the data into the format of TensorFlow dataset, so it can be understood by our Keras model. A minor detail here, starting from this TensorFlow dataset conversion, every code is going to be based on TensorFlow and the Keras library. Now we are going to step 4, build our text classification model on top of the pre-trained BERT. To build a Keras model, you want to subclass the Keras.model class, and because we are taking in an external BERT encoder, we want to add an argument named the encoder into the arg list of the constructor. And we explicitly set the trainable field as true, so that the gradients can be backpropagated all the way towards the pre-trained BERT model. The rest part is straightforward. We have fully connected layer, which is the self.dense one here, and we have softmax classifier, which is self.dense 2 here. And the dropout is a common practice to avoid overfitting. And remember to chain your components together by overriding a call method. It's very simple. You just specify the output of a previous module as the input to the next module. And we are almost there. Last step is to train the model. We want to first have a model instance and do some configurations, like what optimizer will you use, and what's the loss functions you are at, and some metrics you want to pay attention to. And you call model.fit to get a model trained. And this is output of this model training process. We see that within 2 epochs, we arrive at a validation accuracy of around 92%, which is good. But we still see the overfitting problems. Like say, at epoch 3, we see the training accuracy being 97%, but the validation accuracy is only 91%. This is because even though the add-ons, like the fully connected layer, is very small, but the BERT itself is very big. So it has overfitting problem. And that's all for the code. And we have shared this code in the forum. I would encourage you to check it out. And especially if you're interested in building this overfitting problem, you can use this code as a starting point and write your code on top of it. And that's all for the talk. We can go to the question session.
Awesome. Thanks a lot, Chen and Matt, for your really nice talks and careful breakdown of Keras. Got a couple of questions here. Some are a bit technical. So one question is, Matt, you explained this text vectorization class.
Yeah.
I'll just put this in the here so we can see it. So, it kind of looks like a tokenizer in some sense. And the question is, does it or Keras, the library more generally, allow users to kind of train their own tokenizers? So if they're trying to sort of train BERT themselves, could they do this?
Yeah, that's a great question. Text vectorization is going to give you just kind of more basic tokenization. So it'll be good if you want to do like a character level tokenization or a word level tokenization. But if you want like BERT, most of these transformer architectures, you're usually going to want subword tokenization, which text vectorization won't do. But there is a library you could check out called tftext. I mean, for one, you could use the Hugging Face tokenizers for sure. There's also a library called tftext, which you could look at, which will allow word piece and sentence piece kind of inside the TensorFlow graph, which there could be times where you want all of basically your transformations happening inside the TensorFlow graph. So tftext is a way you can do that.
Awesome. And speaking of TensorFlow, the next question is, people tend to use TensorFlow and Keras interchangeably. And I was wondering what the differences are, or when should you use one over the other?
Yeah, I mean, I think the way you can kind of, I mean, TensorFlow is a broad term for a large ecosystem. But if you think of the core TensorFlow APIs as being, kind of a lower level, Keras is a higher level training API layered on top of it. So they're not interchangeable. You can use TensorFlow without using Keras, but Keras is usually the easiest way to build a model inside of TensorFlow.
Right.
Yeah, I think.
Go ahead.
Please. No, I was just going to say, I think TensorFlow 2 kind of, if I remember correctly, Keras became kind of like a first-class citizen. Is that correct?
Yes. Yeah, this is not the case in TensorFlow 1, but the TensorFlow 2, that's the new picture.
I was about to say, in our initial launch of TensorFlow 2, we put Keras and TensorFlow together. So in that case, we have no difference between that, because when you want to call Keras, you just do tf.keras things. And we have split the code outside TensorFlow. The Keras repo is now separate. But mainly speaking, like for people building model, the first place we go to is still using the Keras, because it's like it has the layer and the model abstraction there. It's more closely aligned with the building model process.
Mm-hmm. Yeah, definitely. I totally agree. Like if you want to, build an experiment quickly, you just want to just get done fast. You don't want to, get into the low level, graph and stuff. But I think, from my old experience in TensorFlow 1, using the graph was really great for performance reasons.
Sure. Mm-hmm.
This is maybe more of a philosophical question. So since the transformer architecture took over NLP, do you see a good use for previous models like LSTMs? Because I think, Matt, you showed a pretty nice example, and you kind of answered this a little bit with this, 20K parameter or 90K parameter model, I think.
Yeah, I mean, I think it totally depends on your problem set. But in the example we are looking at, like this, it's a very small amount of data. And you might be worried about doing pre-training because maybe it's a lot of kind of extra data to bring in. It's hard to validate. You might be worried about bias. You might be worried about computational efficiency when you're doing inference. So in this example, the LSTMs actually weren't a great way to go down, but the n-gram models, which are some of the like simplest things you hit in like chapter 1 of any NLP textbook, are actually really, really performant. And it's good to remember they're out there if you do want like a really simple model that you can train that's surprisingly quite effective.
Yeah, I totally agree. I think like one thing we sometimes forget is like, transformers is not like the first thing you should reach for. Maybe like if you're building like a real NLP application, naive Bayes with n-grams is like a really strong baseline. And, you'll often find that the extra complexity, cause you some problems in prod. Let's see. So this is maybe a question for Chen. So there's a lot of optimizers out there these days, and is Atom really all we need, or should we be looking at other optimizers? Because I think you mentioned in your code when you were building the model.compile, you had Atom, And yeah, I know that like there's like a history of Atom and Atom W and all these kind of things, but I'm just curious, like just generally, what do you think about the space of optimizers and
Yes.
where this is developing?
So that really depends on what you want. So if you want to build a state-of-the-art model, Atom is definitely not enough. But if you want to play around with a model or want to try some development work, I would say Atom is good enough. But one thing there, even if you are using Atom, you may need to look at something called moving average optimizer, which is inside TensorFlow add-on. It's just like a wrapper optimizer, but you keep the moving average of the model variables so that it gives you some boost in the performance. That's something you want to look at. But if you're looking at building some state-of-the-art model, maybe you can check out something like SEM, SAM optimizer, and some other like advanced strategy. Atom, I would say like short answer is Atom is still good. But if you are looking on something very advanced, you can think about some other approach.
Awesome. Let me just have a quick look to see what else we have here. Okay, so another question we have is in the chat. Give me a sec. So the question is, can layer-wise learning rates help during fine-tuning when it comes to BERT models?
The short answer is I think it can, but it will be really hard to configure that. Probably you should try a lot of times before you can actually get the model converged. Because if you are fine-tuning with such a big model, it's very error-prone. If you set up like some layer using the wrong learning rate, maybe of some problem. But definitely, at a high level, it should help with the fine-tuning process, but probably not in the aspect of doing the speed of making this work. But just like performance, the final performance could be better.
Yep. Yeah, I totally agree. And this is another final question maybe for Matt. I think in your talk, you were explaining, you had these learning curves or the validation accuracy and so on. And so the question is, can you expand a bit more on this idea of training loss and validation loss? And if the validation loss starts increasing, can we conclude that the model is overfitting?
Yeah. If your accuracy is going down and your loss is going up on your validation set, things can be noisy and you want to look at how much noisy. But I mean, in a lot of our, with the examples I was showing, we weren't doing any pre-training. So we were just looking at this very small data set of 25,000 input examples, which is, it's really, really easy to overfit, at least when you're looking at NLP problems. So yeah, I'm pretty much all of those simple models I showed. If you keep training for a while, notice that you start to be overfitting a little bit.
Awesome. And maybe I can ask the last question. It's a personal one. So working at Hugging Face, I contribute to some of the open source libraries we have here, and there's always this kind of trying to keep an eye out on the future of where things are going. So for example, transformers, there's a lot of developments outside of NLP, and one thing that Hugging Face is interested in is looking at vision and audio. And so you sort of have to make some design decisions about your library, how it evolves, and how do you make sure things are backwards compatible. And I was kind of curious, in the Keras team, where do you see the sort of the future? What are the interesting, say, domains, or let's say even APIs that you find particularly exciting? And maybe you can shed some light on where the library is going.
Matt, do you want to talk about Keras and how people are doing?
Yeah, I think there's a number of things that we're looking at the Keras library. I think one thing we always continue to look at, which separate from this kind of side of the talk, is just how do you easily distribute stuff. So I think one place we continue to have a lot of work is you've written some simple training example, and you want to and as quickly as possible take it to running on a bunch of machines. Doing a multi-work setting, we're always working on that. But yeah, another part that we're looking at a lot is, just kind of bringing in more high-level abstractions for NLP and CV. Kind of giving more of these Lego blocks that we kind of giving a lot more that are specific to those applications to hopefully make it a lot easier to get up and running with kind of more complicated NLP models and CV models, computer vision models.
And one thing I want to add about distributed training in TensorFlow is we are trying to make it even more seamless. Currently, if you write this distributed code in TensorFlow, you need to call some strategy things. I think there is some ongoing efforts trying to trying to make that disappear, like you are going to write the same code, which is called detensor. Like I think it's going to like bridge the gap between like standalone training and distributed training, and hopefully that will be much easier in the future.
Yeah, that'll be like awesome, because I kind of feel that like where we are now as a field, especially in industry, is like there's like a kind of like, you know, different age of like finally you get GPUs at your company. And, you know, like for example, like, you know, in my old job, I was a data scientist and you could get one GPU and you had to share it, you know, with like 3 data scientists. But you start to see that like now that companies are really investing heavily, especially in NLP, that this idea of like distributed training becomes really important, because, you know, being able to iterate fast is in some sense like the way you make progress on your problem. And
yeah,
I think at the moment there's a lot of like pain in like, you know, if you think to yourself, okay, I've got my super nice, say, Keras, you know, lines of code. You said it's not so much code, and now suddenly I want to scale out to like, you know, 20 GPUs, and then I feel like the abstractions are not quite there yet. Like, at least for me, like I feel like it takes a lot of work to build out to that.
Yeah, definitely an area where look at, and yeah, I mean, Keras is really all about that idea. The faster you can iterate is the faster you can like come up with interesting ideas. So we definitely want to be doing that in the multi-worker setting too.
Awesome. So that's it for the questions. And yeah, thank you once again for taking part in this community event. I think it's given people a really great primer for how to train models in Keras and TensorFlow. And we have a TensorFlow scapegoat, as we say at Hugging Face, who's, you know, responsible for building all the API part of Hugging Face transformers, and he's super excited to see more people using this. So thanks a lot.
Cool. Thanks for having
Thank
us.
you.
Thanks a lot for joining.
Hey, so I think we have a few minutes before the next speaker, right?
Yes, so we finished a bit in advance the previous talk, and Matt and Chen were in advance, so we could begin theirs in advance, but well, we were waiting.
It's rare to be ahead of time, right? Usually
Yeah, exactly.
So maybe I could ask you, Sylvain, for people who are interested in like doing projects for the, you know, the next 3 days or the last 3 days of this week, kind of like, you know, what should they know about this? And a lot of people have been asking about the certificate. Maybe we could talk about that for the next few minutes.
Yes. So that's a very good idea. Thanks, Lewis. So let me share my screen again to show you how to go on the forums. So the idea is that we'll use the forum to coordinate team projects. And here it is, the forum again. So if you go in the course category, you'll see that there is a course project subcategory on which you can click, and then you can browse a lot of existing projects. For instance, this one was community contributed, so let's have a look at this one. Sorry, Lewis, I'm not going to pick one of the one you built. But this is going to look like this. There is a small description of the project. There is a model suggestion to fine-tune on that project. There is a suggestion of dataset, how to scrap it from the web, or to use an existing one if it's on the for instance on the dataset hubs. What the challenge is to expect on this project, and what's the desired outcome. And the idea is that this project should go over fine-tuning a model and then create a live demo of it on a Hugging Face space. So let me show you very quickly what a Hugging Face space is. It's kind of a demo of one model. So one that is very popular right now is AnimeCAN V2. You may have seen some of it on social media. I won't be able to show you live what it does because I'm pretty sure there's a queue. But if it loads, it doesn't even, maybe my internet is yeah, another nice demo would be where was the one? Let me go through the organization of the. Is it for the course that you put yours, Lewis? I think
yeah,
it was
that should be
organization.
sentiment analyzer.
The Amazon Reviews demo space. So the goal of the event from Wednesday to Friday is to use the free compute from Amazon SageMaker to build, to fine-tune a model on some data set and then finish with some kind of project like this. So this is a model that's going to predict review score from a customer review. So if I type something like this is a great, what kind of product should be rating, wrong button. Sorry. We should get a nice score of. So does it go from 0 to 1, Keras?
Yeah. So these ones are
Okay.
Actually, this is based on Amazon reviews. So it goes from 1 to 5 stars, and then I mapped them to emojis. So there's 5 different emojis you can get. So
why is it? So this is pretty low. So the model does not predict the right label on this one, or how do you interpret your label?
Yeah, so this is actually one thing that's like challenging when you have a 5-star system, that the models like may get some ambiguity between, you know, on the extremes that will do well, but on the ones that are sort of in between, it
oh no, it just scores a label. So it was predicting a label that was nice. It's just that you chose emoji about, okay, it's not outputting 0 to 5. Okay.
Yeah, sure. Sorry, yeah, it's like the probability, right, in some sense.
Mm-hmm. So it predicted like with 89% confidence that this was a bad review, which is correct. And for the previous one, it was correct as well. So the goal for the rest of the community event would be to build such a space. So fine-tuning your model either in Keras or Pytorch, which is so the general token Keras, also the general token Pytorch next, and build a space like this. So once you've found a project that you like, you should reply to the topic of the project you liked to say, oh, I want to help you build this thing. And then you can go on our Discord server. So I think the address is hf.co/join/discord because you'll be able to chat with your team live there, which is going to be super helpful. On the forums, you can see the first topic that you will see in this category. Since I have already read it, it's not appearing first for me anymore, but when you arrive on the forum, it's going to be first for you. This topic is going to explain all the rules of the community event. So you should gather into teams of up to 4 people to create fine-tune your model and then create a space. This is all that's required to get the certificate of completion. You have to create your space before November 24th, and the space needs to be working. One member of the Hugging Face team will double-check that space outputs proper results, and then every member of the team will get the certificate. So we have created a few ideas of projects in this category, and you can create a new project by creating a new topic yourself, just like the person project I was highlighting before. And then we recommend using fine-tuning for your projects, like not trying to pre-train a full model on a new language, because that would require lots of data and lots of compute, which you may not have time to finish that before the deadline of next week. Fine-tuning an existing pre-trained model is going to be way faster for that. And so Amazon is sponsoring the event by offering free compute from Wednesday to Friday using AWS SageMaker. You will learn how to use that tomorrow with the Hugging Face talks that are more focused on how to do things than more general talks are on the landscape of transformers. So you will have to file a form. You just have to click here for the link to get access to a special AWS account. Don't worry if you don't hear from AWS before Wednesday, because the account will only be created on that day. And you should join the Amazon SageMaker community organization, because all the models that are pre-trained using pre-compute need to be hosted there once they are trained. So if you didn't register for the event in advance, you should see a button. I'm a member, but you should see a button somewhere here to ask to join that organization, and you just have to click on it and accept you. And of course, you're welcome to use your own GPUs and cloud provider if that's your preference, but that's not going to be free. And then you can, as I said, you can live chat with your team members on our Discord. And then if you have any question that's more general and to which the answer could benefit the whole community, you should ask it on the main forums. so that it's more visible. But that's pretty much it for the rest of the event.
Yeah, and I think just one thing to mention, if you have an idea for a project yourself, you're more than welcome to propose it. So we have a list of kind of ideas, but if you have something that you think is cool, just chuck it in the forum and go ahead.
Yeah. Oh, and I see that Mark just joined us. So I'm going to remove my screen. And so, so our next speaker is Mark Saroufim. Let me add you to the stream, Mark. Hi, Mark.
Hi, everyone. How's it going?
We're doing well, thank you. So Mark is a partner engineer at Pytorch, working on open source software production tools, including TorchServe and Pytorch Enterprise. And Mark was also an applied scientist and product manager at GraphCore before Yuri.ai, Microsoft, and as GPL. His primary passion is to make programming more fun, and today Mark will explain to us how to train a model with Pytorch. If you want to share your screen, Matt, I can then post it. And then like before, you should go on our forums to ask your questions. And I've also put the link to the Collab notebook for Matt's talk there.
All right. Thank you so much, folks, for having me. So I guess like today's talk is really going to be about like how to train a model with Pytorch the hard way. So I suspect a lot of you may have seen some of this content, but rest assured, if you've never trained a model with Pytorch, you'll be able to understand this talk. And if you have trained a model with Pytorch, the talk is going to be different enough, and the take is going to be more focused around the internals of Pytorch, so you'll still get to enjoy it. So please stick around, and if you have any questions, feel free to let me know. We'll be just monitoring chat. So basically, this talk is going to be about how to train a model with Pytorch the hard way. And just like a bit about myself, like the projects like I work on at Pytorch are like model inferencing tools like TorchServe, model like ML ops tools like TorchX, and then like long-term support branches of Pytorch with Pytorch Enterprise. And if you do enjoy this talk and enjoyed like stuff I'm saying, go ahead, follow me on Twitter, and just feel free to DM me with any questions you have. So what we're going to be doing right now is just like really from scratch. We're going to just start off with importing Pytorch. And before we get to training a model, I just thought like it'd be helpful to just discuss very briefly like what is really machine learning. And really the framework we're going to be focusing on today is called supervised learning, where you can imagine that you have like some data, and then you want a model to make a prediction on that data. So if your model is a function f, and then your data is some variable x, then the prediction is y. And the way all of this stuff is really going to work is that you're going to make a prediction, but then you want to compare it to like some labeled data. So like the truth, let's call that y prime. And based on the difference between y and y prime, which is people often call the loss function, we're going to update f. And that's pretty much it. So as long as you can fit problems in this framework, you can train a model and solve problems with it. And in general, as a helpful heuristic, when you're trying to think about like, well, what is really solvable by machine learning, you can think of X as just something something that can fit in an Excel spreadsheet, like whether or like whether it's like or also like an image or text. But really, fundamentally, it's like some data, and then there's going to be some column that you're trying to predict, and that's your label. So really, though, the topic of this tutorial is going to be how to train a model, right? But before you train a model, there's lots of stuff that you can do. So this is sort of training a model is really sort of the last step that you should explore. So one is you could use something like an open data set. So instead of you labeling data, you can go use something like IMDb, ImageNet, or use something from like the Hugging Face data sets. Instead of creating and training your own model, you could use an open model. And what I mean by that is you could copy a model architecture from some famous paper on GitHub. Well, not only can you just like pick an architecture, you could also take in the model weights. So as in you don't even train a model, there'll be like a pre-trained model with things like the Hugging Face hub or Torch hub, where you basically just have a function itself and then make an inference directly on it without needing to worry about like updating it. Also, like lots of like tools that make models like libraries like Pytorch easier to use, like the Hugging Face training loop, like the Pytorch lightning loop, like the Ignite loop, like the Fast AI loop, or even Keras if you're in the TensorFlow ecosystem, all make it easier to do this. And so what we're going to do is really going to unpack like how these trainers like actually work and how you'd implement them in raw Pytorch. So like I said, this is going to be like the focus of this talk will be how to train a model. So fundamentally, though, like before we start talking about like how to do machine learning, a lot of these training loops look something like this. So you'll have some sort of model, and then you want to fit it on some data, right? Then you have like tools like AutoML where you don't even worry about the model, you just like fit some data. And then like pre-trained models where, you know, like you just essentially fine tune on some data. So that would effectively be like calling something like fit. So this loop, so let's just show you an example of what this looks like. So for example, I'm gonna install transformers here very quickly. And what we're essentially going to do here is we're going to use a model by the DeepSet AI team. So they have a mini LM model. So this is a small language model on a question answering data set. So as you can see, I'm literally just downloading the model here, but also downloading like a tokenizer for it. So as a tokenizer is because essentially neural networks like don't really understand like what a sentence is, right? So for example, let's say we want to ask the network a question like, is Mark clear? So we want to tokenize the sentence into a bunch of numbers that a neural network can understand. Essentially, the way this tokenization will work, this is like a word piece tokenizer. So it'll take basically every word in that sentence. But then what we really want to do is return tensors from it. So we want to make sure that these are all basically data that the neural network can understand. And so this is exactly what this looks like. We're going to tokenize this sentence, and we're going to basically, and then we're going to make the model do an inference on that sentence. And essentially here, the model is going to make a whole bunch of predictions, and we want to find the most likely prediction. So we're going to do an argmax over all the predictions, and it's going to say, no, Mark is not clear. Actually, here, what is my name though? Because this is a yes or no model. But so this is sort of like the general idea behind this is that you can think of your model as just a function on top of some data. So that takes in some data and gives you a prediction out. And so the question will be, how do you train a model like this? So before we start talking about Pytorch, it's helpful to just go like, you know, back to like the titans on which like everyone stands on, and that's something like scikit-learn. So imagine that you have some data, and then this data is literally just like on a 2D plane. So you have the 0.11, 0.12, 0.22, 0.23, and you want to basically fit a line on this data, right? So the question is here, well, you know, how do you do this? And so if you want to fit a line, like one way to do this within scikit-learn is to just call like linear regression, and remember fit. And then, so X is the training data, and then Y is are the labels. So we train a model, and then let's say you want to get the accuracy for it. You know, turns out that it's a perfect model. But then if you actually want to figure out like the quote unquote like model weights, this would be like 1, 2, and then the intercept. So this is basically the A's, right? So if you have like Y is equal to AX plus B, so A is a vector in this case, and then B is a value. And so this gives you like the function. But trying to get back to this analogy when we were talking about like a model is just a function. In this case, if you said like, for example, I want to predict the value of the 0.35, then this would just here in this case like return a single value of 16. So again, so in this case, like we have a function that takes in like 2-dimensional data and returns a 1-dimensional output label. It has weights, as in, you know, this is 1, 2. So let's say, imagine you save those to disk, and then you can load them again, and now someone else can use this model. You can deploy this model. So very much so, like you'll notice, like in frameworks like Pytorch, that you can think of like your model as being like a data and a function. As in, it's data when you save it, but it's a function when you're doing an inference on top of it. And this is a very powerful framework to think about it. So back to talking about like training loops, you know, so here, for example, in this case with scikit-learn, we had this like linear regression.fit xy. But let's say we use a framework like Pytorch Lightning, but again, like the same idea applies to whether using the Hugging Face Trainer, Ignite, Keras, Fast AI, like the same idea all applies. So we're gonna have like some model, and we'll describe what that is in a second. And then what you're basically gonna do is call a trainer fit on a model and some training data loader. So this is some data, and then validation data loader, just to make sure that you're not overfitting on your input data. But it's sort of the same idea, right? Like model data. So what's a training data loader? Well, a training data loader could be something like it. So in this case, it's a function that applies to some data. So for example, it could be like here. So let's just go over this example. So let's say you have a CSV data set or an S3 bucket or some binary data or links to images or whatever. You want to be able to, for example, like load in a few examples at a time. So instead of just like making the trainer take in some raw data, you make it take a function that has access to that data, but can put it in a nice enough format for your trainer to work with. So there's a whole bunch of data loaders that exist. Like a recent one is like Pytorch also has a data loader that works well with like sort of internet data, as in an S3 bucket where you're streaming stuff. So definitely a super convenient way of working with data. So this is how so here, remember, so there's to really understand this function, this trainer.fit function, there's two parts. There's the model part, and then there's the training data loader part, and then there's the fit part, right? So actually, sorry, three parts. So we covered the training data loader. Next, let's cover the, next, let's cover the fit part, right? So the way this works is, so remember like when we described like machine learning in plain English, like you make a prediction with some model, and then after making that prediction, you want to see how different that prediction is from the actual example. And then once you know what that difference is, you update your model. So this is going to be exactly that. So you have this first like training step here. So first off, like we're going to be iterating over like examples from the data set. You're basically going to figure out like, well, how different was my prediction from the prediction of the model. So this is what this training step is. Then you're gonna basically, so this is just figuring out an inference. And the backward step here, what you're gonna do is figure out like by how much should you change your model weights, and then apply this change in model weights here. So if this seems complicated, this will make a lot more sense when we're discussing like real code. Like this is just pseudocode at this point. But again, in plain English, the way to think about this is you want to figure out how wrong your model is. That's your loss. You want to figure out by how wrong each layer is. So that's loss backwards. And then you want to update your model. So that's optimize your dot step. So understandably so, you may think at this point, like, well, you know, like, why should I bother to really train models from scratch? Like, I can just use a pre-trained model and not have to worry about any of this. And you're right. Like, I mean, for 99% of use cases, like that's definitely true. But there's a few reasons why you may want to train a model from scratch. So the first one could be, well, you know, if you're using a pre-trained models and you know, you have a whole bunch of failures with it, it'll help you debug things more easily. Also, you can do ML research more easily. Sometimes you don't have a choice. Like let's say the kinds of model or the kinds of data sets that you're working with just don't exist and you need to do everything from scratch. And fourth, it's fun. You know, it's a fun skill set that can help you get paid a lot. So it's definitely like worth investing more in it. But really, you should think of this as being like over time, you want to make sure that like machine learning model training doesn't become sort of like this arcane like knowledge that like only a couple of mages like know about. Like it's actually not that tricky. Like once you get to the basics of it, and hopefully this talk like makes a lot of those points a lot more obvious to you. So great. So we've done all of this. You know, this last 15 minutes was all introduction, and really, you know, now we can finally start talking about Pytorch. So what is Pytorch? Like, what's the difference between Pytorch and scikit-learn? So the main difference is that like Pytorch is what's called a tensor computation library with strong GPU acceleration. So tensor computation means it's not that different from NumPy, but with strong GPU acceleration is like one distinguishing feature. And the other main feature is it adds facilities for tape-based autograd systems. And again, this is just like a very fancy way of saying that you can take a model and then figure out like how wrong each of its layers are without necessarily having to do like a whole bunch of calculus yourself. So this is sort of like the primary benefit of Pytorch. So let's go over an example, right? So let's say, so all Pytorch models need to inherit from a class called like torch NN module, and then they'll have an init function and a forward function. So in the forward function here, you're going to see that, well, we have this linear layer, and then what we're calling a nonlinear layer, and then a linear layer and a nonlinear layer. The reason we do this is because if you have two linear layers one after the others, they'll just collapse into a single linear layer. And if it was just a single linear layer, great, you end up back with linear regression. So the example we just covered. So the main difference with deep learning is, one, it adds nonlinearities, and I'll show you in a sec like how those work. And it adds linearities, and then it also adds like nonlinearities, and then it has like facilities for you to do autograd on top of it. So you don't need to think about how to update the weights of this model. And if you're just wondering, like, okay, well, what do you mean by these linear layers and activation layers? The linear layers here are, for example, torch and then linear, and this is literally just linear regression example, and then torch, ReLU, and softmax, and I'll show you in a second like what those are in a second. But we have this model, great, it compiles, and then great. So now we have this model here. So let me just show you what this looks like. So if you print it, great. So this is like what the model looks like serialized. So this is sort of the data structure that you're working with. So you may have heard of other kinds of layers. So you may have heard of things like attention, RNNs, recurrent neural networks, convolutional neural networks, but they're all sort of almost like special cases of linear layers. So that's why I'm really covering it here. So attention, for example, and so attention is really just like includes like 3 linear layers, and there's like other better talks that go over like how this works exactly. Recurrent neural networks also include linear layers, and convolutional neural networks aren't really upfront. They don't really look like linear layers, but you can implement them as such. And the reason why we have different layers, just to be clear, is because they have what's called like different inductive biases, as in that's just a fancy term for they're good at certain kinds of tasks. Like CNNs are good at finding like information in a space. RNNs are good at remembering stuff. Attention is like, I guess at this point, good at everything. But foundationally, in terms of ops, like thinking in terms of linear layers will help simplify this like quite a bit for you when you're thinking about these for the first time. Okay, so yeah, so here we printed a model, and just the thing to keep in mind here is that really what we're doing is very much like matrix multiplication. So let's just like look at this thing like very quickly. So we have this linear layer, and it's saying, okay, it's taking in features 100. So that means it's taking in a vector it's taking in a vector of size 100. But then it has like these hidden features, like the out features and the in features that are higher dimensional. That way you can sort of represent your problem using more than just like 100 weights. At the very end, you'll notice that it has like this out features 10, as in, let's say we're predicting like one of 10 classes, like one of 10 possible animals. So this is where this shows up. And the softmax is really just a way to pick the best, like basically the best feature among those 10. Right, so let's say each of those 10 will be a number, and I'll show it to you in a sec. And then you just like want to pick it. So again, the way to think about this is, what is your input size? Output size, like basically the hidden feature size is basically how much compute can you afford, how much storage can you afford. Out features is determined by your problem, like how many classes you have. And then you're going to have some nonlinear function like the softmax that helps you pick the most likely class. So just to show you, like there's no black magic here. Like let's say we had the ReLU, for example, and like what does this do, right? So let's say we generated this like random tensor. There's a very useful function in Torch, like rand_n. So it generates a random tensor of size 4. And what the ReLU is going to do is it's basically going to zero out all the negative values. So here you see these 2 are negative, so these are just going to be 0. And then this one remains unchanged, right? So this is just like a way of getting rid of negative values and make sure that like your models are more likely to converge. As far as softmax goes, notice here, so I said this thing earlier that like softmax helps you pick the most likely value. And again, that sounds like it's a bit like black magic. But the way to think about it is that let's say you have 4 possible values for like a prediction. And what you want to do is you want them to become a probability distribution. So you want the sum of all of those values to be equals to 1. And then you would basically generate a random number between 0 and 1 and pick one of these. And then you'll see here that if you sum them up, it's actually pretty darn close to 1. It's just it's floating point numbers, so it's going to be hard for them to sum up to 1. But this is how you would get the max, right? So then let's say you want to figure out like which of those values does your model predict, you would do something like np.argmax on top of the sum, and it would tell you, for example, that the most likely prediction is this guy right here. So like label 0, right? And then label 0 could mean cat, dog, or whatever else. So there's another key value story that you would have to keep track of these things. So let's just quickly go over like how these look like exactly. So there's this nice library I like called like Rich that shows you like how to inspect modules, and like torch functions are the same. So for example, relu here, you want to apply a rectified linear unit function element-wise. So this means element-wise means you're applying a function on each element of a tensor. And there's like vectorized versions, there's like broadcasting, there's all this cool stuff that we can talk about. But in general, like looking at the docs is honestly really helps sometimes to figure out how something works. Whereas like with torch linear, the way that works is it's saying you apply a linear transformation to the incoming data. So you have y is equal to xa transpose plus b. So a is a vector, let's say how many inputs you have, and then b is some sort of bias, just so that you can like move around the function. And then y would be your label in this case. So again, looking at softmax here. So it's saying it applies a softmax function to an n-dimensional input tensor, rescaling it so that all the elements are in the range 0 to 1 and sum to 1, right? Again, remember now, like back to this model right here, this tiny model, that's a toy model that we have. Remember when I said that like models are functions, but they're also data. So let's say I want to print the values that are like in these weights. Like you can just literally print them like this. You can just say for param model.parameters, and you can just like print them and like visually inspect them to see what's going on. Like maybe you have lots of nans, which is like bad, right? But you could also like look at, for example, the parameters per single weight. So for a single layer. So let's say I want to say for model.params. Oh, sorry. Yeah, getting lost here. Yeah, so for model.linear1, so linear 1 was the first linear layer. You can also look at the params, but any layer is sort of the same. And so again, and that means you can save it, you can load it. And so this is how like a lot of ML ops gets done, and that like you train a model, you save it, you load it again, you can use it for something else. And the reason is because like, again, it's both data and the function. So, you know, like I said, there's all sorts of other architectures like transformers, CNNs, recurrent neural networks, and you can sort of dream your own. And a great way to actually learn Pytorch is to go ahead and try to implement one of those things like from scratch, right? Like, and just see what would it be like. Let's say, so right now we're with our Hugging Face, like Hugging Face course. So what would it look like to implement like a really simple example of like of an attention layer? And you can sort of do this like building it up with linear layers, but obviously like a production ready version would include like so much more stuff, but at least it gets you like more familiar with the basics. So other things like, so let's say we talked about softmax, which is a way to make sure that the values in a vector all sum up to 1. But there's a whole bunch of other ones. For example, there's one called like a Gelu. And then just like looking at this thing, you know, you could be like, okay, like you could sort of try to understand like how some of these things work. There's like the swish function, also the same. And the nice thing about experimenting with ML, so back to the tiny model here, a machine learning is inherently like a very empirical science, right? So instead of like, let's say trying out a softmax here, maybe you could try out a Gelu, maybe you could try out a swish. You could come to the linear layer, make it bigger. You could change it to a CNN. You could change it to an RNN. So it's like very Lego based. So try things out, and then you can just see what works best on your problem domain. And if you don't have time or don't have the expertise to do so, that's where using pre-trained models like really, really helps. All right. Excellent. So now, like, I guess it's time to talk it like, you know, in a bit more detail as to like, what is a tensor exactly? So let's say we have this thing called A. So it's going to be a torch rand n. So that means it's going to have 5 elements, and then they're going to be allocated on the CPU. So let's inspect this for a second and see what's interesting here. So one, you'll notice like data has a D type here. So D type means it's a floating point 32. This could have been a floating point 64 as well. The reason I want to talk about like D types here is because let's say if you're using like NVIDIA GPUs, then you may use something like a floating 16. If you're using like an Intel CPU, you may want to use something like int8. So turns out like precision, as in like very precise numbers, doesn't really matter drastically for machine learning. So you can use lower precision bits and take advantage of hardware acceleration. So if you want to take advantage of that kind of hardware acceleration, like all you would really need to do is come in here, for example, and let's say add in like dtype equals like torch.int8. And that's pretty much it. Like Pytorch takes care of the rest for you. But there's other also interesting stuff. For example, like MKL or ORT. So for example, is it using like the Onyx runtime environment? Is it using some acceleration by Intel? Is it using Vulkan? What's the layout of the tensors? Like is there like a specific way it's laid out into memory? Does the tensor have a name? What's the type? Like maybe it's a complex tensor because you're doing something with music. Like what's the shape and what are the actual values inside of it? So this is like the tensor is sort of like the main data structure that you're going to be working with. And again, just looking at its arguments will give you a lot of ideas as to like what's available and what you can do with it. So back to how to make an inference though. So let's say you have this network, right? And now we want to print it. Like again, this is what this model looks like. And I want to just generate, so here it says in features is equals to 100. So I'm literally just going to generate random data. So input touch random. And then I'm going to make an inference here. And I'm going to print the output, right? So this is sort of like when you're thinking about like what is like inference, or just like you have some data and you want to pass to a model. Like this is the way it works, and this is how you would know like what the input dimensions are. So that's pretty much it, right? But let's say now like, well, we're doing classification, right? So we want to figure out like what is the maximum value between these things. So we know, okay, that the largest value is this like 1325 here. And that this corresponds to index 1 because it's 0 indexed. And this is how you can end up making a classification from just like the super simple prediction on raw data. But in of itself, this is not super interesting because we just have random model weights on some random data, and we got like, so we have garbage into garbage out. So like none of this is interesting so far. But it shows you again like how the framework works, and now we'll do something a bit more useful here. So remember when I talked about that when you're trying to train a model with Pytorch, like the things that you need to think about are your model. So your model includes like some layers. So these could be linear layers, they could be CNNs, they could be RNNs, etc. It includes your activation function. So like maybe it's softmax. Your goal, which really you can think of as being the loss, as in like, I want you to, for example, make these accurate like predictions. Well, this formula, the categorical cross entropy, like really helps. But you could have like all other kinds of formulas that make more sense for your use case. And then the optimizer, you can think about it as how can you achieve your goal. So the most popular way is what's called like stochastic gradient descent, but there's other algorithms like Atoms, and there's a whole literature on optimizers. And most of the reasonable ones already exist, like in Pytorch. So you can, again, just try them out and see what works best for your use case. So in terms of here of an optimization, what we're going to do is we're saying, okay, we want to do a classification. So that's why we're using cross entropy loss. And we want to perform stochastic gradient descent on this network, basically the net dot parameters. We want a learning rate, which basically tells the model like how quickly it should update its weights. So for example, if it's converging too slowly, you make this value bigger. If it's converging too quickly, or if it's too chaotic, then you make this smaller. And then a momentum is also like slightly more advanced concept, but that also helps with like convergence. So remember when we talked about like Pytorch here? So we said, for example, that if you want to generate a random tensor that's like, let's say of size 2, it's going to generate 2 values. But let's say we want to generate a tensor of dimension 3, 2. So this basically means you're going to have like 3 tensors that are of dimension 2 stacked one on top of each other. So another way to do this could be like, let's say instead of it being a tensor, it could just literally be like a list, right? And you just like append them one on top of each other. But the benefit of doing things in a batched way is that like now, let's say you want to make 3 inferences. Instead of like, let's say adding like a model.out on a for loop, you could basically make a batched example, and then you have a single operation that can run like really fast, like on GPUs. So this is again where the NumPy with GPU acceleration pitch of Pytorch comes in. Most numerical linear algebra libraries also come in with like a bunch of nice stuff. So let's say we have this batch here, and so this is a matrix of size like 3 by 2. And then we're going to multiply it by a value 2, right? But 2 isn't a matrix, right? So if you said 3 by 2 times something of size 1, like that operation should fail. But Pytorch here understands like what you mean, and what it does, it'll broadcast this 2 into a vector for you, and then multiply each of those elements like by 2 for you, because it's sort of like understood like what you're trying to do here, right? So again, so this is like where using a linear algebra really helps. Like whereas like you could use something like Python lists, but you're probably going to have to re-implement all this nice stuff from scratch. You may not have like the nice like GPU acceleration. You're not going to have like all the core ops like either an A10 or BLAS or etc. like implemented for you, and you can just like work in Python as opposed to working like with C++ functions or Fortran functions, which is like not super fun. So back to this batch example. So let's say I create an example that's like now 3 by 1, and then I have like, let's say this is my B batch, and then my A batch was 2 by 3. So because the dimensions match and the inner dimensions match, you can multiply these two things. So one of the reasons why GPUs are so important for machine learning is that they're very good at taking in like these large batches and multiplying them very quickly with specialized kernels. So thankfully, I mean, like GPUs aren't like that expensive anymore, like especially like with something like Google Colab. Like all I really have to do here was come in here, click on edit notebook settings, choose a hardware accelerator as a GPU, and we were pretty much good to go. So let's say, okay, so now let's try to do like more of a real use case, where let's say we have a batch size of 5, and then we have 10 classes. So now like the random tensor that I'm generating, let's say again, like I haven't changed my network. Like my network still takes in an input size of 100. I'm going to say, okay, well, you also need to be taking in a batch size of 5. So I'm going to have 500 size tensors like stacked one on top of each other. I'm going to put them on a device called CUDA, so that basically Pytorch knows like, okay, you're going to do something on a GPU. I'm also going to say requires gradient equals to true here. And then I have like my target here, which is basically going to be, let's say like the D type is going to be torch long in this case. And then I'm going to generate like 10 number of classes. So I'm going to generate like 10 random labels. And then the way Pytorch would know how wrong I am is essentially here with this function. So like if you go back to criterion, right? So criterion here is the cross entropy loss, right? So what I'm going to do is I'm going to take the cross entropy loss between what my inputs suspect and what my targets are. So basically my inputs and how wrong I was. So just to quickly sanity check and look at some of the shapes here. So yeah, so this may take a while. Let's see here. Am I on GPU? Maybe I should have made this smaller. Let's see. I ran this before. Anyway, like so while this runs, like let's just give it a second. Okay, it ran great. So you'll see here that the targets.shape, for example, is going to be here. So let's see, number of classes. Let's see, targets.shape. So here the targets of shape is going to be, there's going to be batch size many examples. So basically, we're going to have like 5 examples that we're predicting from, right? The input shape is going to be the batch size times the input size, so 500. And in this case, you'll see the loss is actually a number. So this is a number that tells us like how wrong we are. And you may have guessed that ideally we want this number to be as close to 0 as possible. And this is exactly where, now like the training part really starts. So let's do this. So we have this tiny model, and I'm going to send this model to the GPU. Then I'm going to have a criterion. So I'm going to say, okay, I'm going to do a classification. I'm going to have my optimizer. I'm going to do 5,000 epochs. So basically, I'm going to go over my data 5,000 times. And pretty much all Pytorch training loops look something like this. First, make sure that you basically zero out like how wrong you were from earlier. That's what the optimize your grad is. You calculate your current output. So this is what's called the forward propagation. You figure out how wrong you were. You get the gradients on how wrong you were. And then you basically apply an update to your weights. And then you start printing the loss. And ideally, you want this loss to go down. So let's see if this actually works. Okay, for example, here we're starting with a loss of 232, 229. Where we go? Yeah. So we started with 232, 229, 222, 213, 1.97. So you'll notice, by the way, that even though we did 5,000 epochs, and all we're doing is training on a single example, like basically a single like fake example, and we have a model that has like a hidden layer of 1,000, even then we weren't able to get the training loss to 0. So generally doing random data helps because it helps you debug errors before you start working with real data. And it just goes to show you how hard some of this stuff is and like why you should maybe sometimes consider using a pre-trained model or using like an open model with like with things that are known to work. So how would you make this loss 0? Well, maybe just try more epochs. Maybe try making the hidden layer larger. Maybe try adding more hidden layers. Maybe try adding like different kinds of layers. And just try stuff. And eventually you're going to find something that works and maybe you'll learn something new out of it. So again, because ML is a very empirical discipline, the faster you get at experimenting quickly, the better you're going to get at learning what actually works. So this was as far as the training loop goes. So I'm going to repeat it. Like you zero out how wrong you were from earlier. You figure out like what is your current prediction, how wrong that current prediction is. You apply how wrong you were on the hidden layer on each of the layers. You optimize your model, and then you basically print out the loss. And then you want that to go down. So this loop will serve you well, and everything will sort of like look like this. Unless you're using a training loop, then you obviously won't see this because someone else would have done this for you. So let's talk a bit about gradients, right? Like how does this magic work, right? So we had this thing on optimize zero grad, we had loss backwards, and we had optimizer that step. And really the point I want to make to you is that there's no real magic to this. Like as in, instead of using the categorical cross entropy loss, like I could have just computed this loss myself, and then I could have seen, okay, well, I have this loss, it's on this device, etc. And even then, like when you're thinking about this optimizer.step function, really the way it looks is like this. Like you basically, you go over a bunch of epochs, you figure out like basically some gradient on a vector, you apply a learning rate, and then you sort of successively apply it over and over again. So it's an iterative algorithm. So again, like none of this is any black magic. But let's talk a bit about the black magic, which is really automatic differentiation. So let's assume, let's forget like the tiny model for a second. And let's assume that you have something that looks like this, which is you have let's say here. So let's say we have a tensor that's just like 2, 3. And then this tensor that has like the values like 5, 6. And then we're going to create a tensor. So that's basically 3a plus b times a. Right? So this is a function. So before we run this, let's look at a bit about like the calculus for it. So let's say we have 3a plus ba. Let's say you want to derive this with respect to a. Then you have 3a, then that's 3. And then ba, so then the derivative is b. So then you know that the end value is going to be 8, 9. But now let's say you're deriving this with respect to b. Well, 3a is not a function of b, so it's going to be 0. And then here it would just be a. So then great, then the value is just 2, 3. So let's just confirm that that's actually what Pytorch does. So here we're going to basically have a place to deposit the tensor. So think of it just like as a data structure where you're putting the gradient updates. And then we're just going to say c dot backwards. And when you do that, you're going to notice, okay, so it's 8, 9, 2, 3. And that matches exactly like 8, 9, 2, 3 here. Okay, so this is it's complaining because I'm doing this twice, but this is fine. So again, like when you're thinking about how to use Pytorch for automatic differentiation, part of it is that like if you have a large complicated model, computing all the derivatives for it is really annoying to do it by hand. So you can sort of convince yourself that it works on some simple functions, but if you have like much more complicated, what's called like computational graphs, like neural networks, this is where using an autodiff engine will really, really be helpful. But you can always sanity check, like what are the derivatives exactly if you look at a.grad, and just sanity check them by hand to make sure that everything works great. So once you've done this, like you finally trained a model like success, what you could do is you could just save it with like, you can just say like net.stateDict and save it to some path. And then at that point, it'll just be like data that's stored on disk. So you can upload it to an S3 bucket, you can put it in an Azure blob, you can send it to your friend by email on Dropbox or whatever. And then what they could do is they could call torch.load and load it. And then if they were to print it, yeah, great. Like they just saw like the exact same model that you got, and then they could again do for load for param and loaded model.params, and get exact what the parameters are, and then call loaded model on an input and do it for whatever they could call it, and then fine tune it. So again, this data as a function paradigm is really the one thing you could take away from this talk is that will help you really like grok how this stuff works. So that's really the main thing I want to cover today, and I really want to end like with a slightly more advanced feature. It's been very exciting, which is TorchFX. So Pytorch, even though like as a user you're mostly using Python, but Pytorch is actually mostly written in C++ because it helps us like memory manage and write things in a more efficient way in general. One exception to this is FX. So what FX is essentially a way to write compiler passes over Pytorch modules in Python. And the reason this is very powerful is, so let's go over an example here. So we're going to basically load in a model. And what we're going to do is you'll see we literally have a for loop. It's like, oh, for node and graph.nodes. And what we're going to do is we're going to say if node.target is equal to linear1, make it linear2, right? So what is this effectively? Let's look at the model again. So we have linear1, we have activation. Then we have linear2, and then we have softmax. So what we literally did here is we skipped those first two layers and created a new model. And now this new model, we can save it, we can fine tune it, right? So again, this is sort of just the tip of the iceberg, but I really wanted to show you this example because you could do all sorts of stuff. Like maybe you want to export your model to some runtime like TensorRT or RT. Maybe you want to quantize your models as in change the D type to an int8 or float 16. Maybe you want to do something like extract intermediate representations of a model. Maybe you want to fuse two operations. So if you have two operations that show up a lot next to each other, you can create one single operation that's much faster. And there's a whole bunch of stuff you can dream up. So this is probably a very, very fruitful area where you can think about how to innovate within the Pytorch ecosystem. So like really in conclusion, maybe in the not so distant future, like model.fit or just like model.finetune will be all that you need. And at that point, like knowledge of how to train networks from scratch, like may be lost. But what I'm really hoping is like, let's say, like the four horsemen of the apocalypse, like descend upon us, and that we lose all pre-trained models and that we lose like all open data sets, is that like the knowledge of how to train like models from scratch gets maintained, that you'll still use it, that you'll still build innovative stuff with it. And at this point, you may think, great, like this was maybe a great or maybe not so great like introductory talk as to how to use Pytorch. So if you're really interested in learning more about Pytorch, what I would highly recommend is you read the docs. The docs are great, probably some of the best tutorials. And the other step is reading good code. So there's lots of good code around, like whether it's by people like Phil Wang, like Ross Whiteman, Matthias Fay, but also highly recommend you just check out like some of the source code for Hugging Face or Fast AI. You'll learn a ton about how to write like good Pytorch. And even then, if you're thinking, great, like I want to do some more advanced stuff, or maybe I even want to work at Pytorch, probably the best way to contribute to Pytorch is to solve issues on GitHub. So we have lots of issues tagged with beginner or bootcamp tasks, so you can check those out, and you can create like a cool project with this. So try to basically create something cool to get like the attention of a Pytorch developer. But really, most importantly, is like follow the gradient of your interests. Like as in, like this is a big field. There's a lot of interesting stuff you could do. So if you do something interesting, you're much more likely to do something else that people find interesting. And if you have something cool and you want feedback on it, like feel free to DM me. I'm more than happy to share feedback on it. And I guess that was it for me. Thank you so much, folks. If you have any questions, I'd love to take them.
Awesome. Thanks a lot, Mark. That was a super comprehensive tour through, I'd say, almost all of ML. So great. And in fact, it reminded me a bit of Jeremy Howard's What is Torch NN, really. He has this super nice tutorial on the Pytorch docs where he kind of deconstructs all this stuff from scratch. And I sort of saw you also channeled Richard Feynman at the end, where he had a similar analogy in physics that, imagine we lost all knowledge. What would be the one idea that you would like people to remember? And he was like, matter is made of atoms. And for you, it's like, know how to train neural networks from scratch. So,
yeah, I'll say probably matrix multiplication and autodiff. I think those ideas would help us rebuild significant chunks of civilization. But thank you. Like, I don't think I'm worthy of those compliments, but thank you.
So I think we've got time for like a couple of questions. So one thing here was you mentioned at some point this sort of kind of technical detail about not needing high precision bits in machine learning or maybe deep learning in particular. Could you sort of expand a little bit? Why is this, and why should I care?
Sure, yeah. So I mean, so this is maybe more historically, but if you can imagine, like maybe the first like scientific use cases of computers historically were things that were very calculus heavy. So imagine like ballistics, like nuclear simulations, so hard science stuff. And typically in hard sciences, like the lower precision bits really matter, like because if you're off like by a bit, like your rocket like won't land. You'll attack someone you don't want to attack, so it's super important. In machine learning, like just it's like I don't know if I have a good theoretical argument as to why this is the case. Like all I can say is anecdotally, if you do try to deploy some model or train some model with lower precision bits, they tend to do not that much worse than the higher precision ones. The benefit of it though is like you're definitely losing some performance, but you're gaining more in terms of hardware acceleration. So like hardware providers will give you like better kernels to do things really fast. So it's definitely a conscious sacrifice that you're taking. But for a lot of people, it's worth it. And it could be worth it for a few reasons. Like let's say for inference, you just want your inference to go faster because you're doing real time. So that's a great reason to use lower precision. But even for training, like let's say you're debating between, okay, I want to train for 1 week with floating point 32, or train for 1 week with floating point 16, so I'm effectively doing twice the amount of training. That may be worth it because just like time is limited on this earth, right? It's the only rare resource that we have, and so it's just a thing to consider. So the argument is purely, as far as I'm concerned, like anecdotal, but I'm sure some people that are smarter than me know of some theoretical reason why that's the case.
Awesome, thanks. So I think we hit the time. So thanks again once for giving this awesome talk, and thank you for contributing to the course community event.
Well, thank you, Lewis. Thank you, Sylvain. I really appreciate it. Thank you for listening, everyone. Appreciate it.
Right. Great. So I think we have our next speaker here. I'll just add. Hey, Jakob.
Hey.
Cool. So it's a pleasure to introduce our last speaker. It's Jakob Uzkorai. Jakob is the co-founder of Inceptive, which designs RNA molecules for vaccines and therapeutics using deep learning to make RNA-based medicines more accessible. And for those who maybe don't know, Jakob was at Google for more than a decade, and he kind of knows a little bit about transformers since he was behind the groundbreaking Attention is All You Need paper. And so we're really excited to have you here to tell us what is maybe not so great about transformers. We've heard all these talks today about how transformers are like amazing and, you should just go use them and have fun. And I think here we're going to get some kind of cold water maybe on board. So looking forward to it. And if you want to stream your slides, you don't have slides, right? You're going to do it in the background, right?
Exactly.
Awesome. So we'll be here, and I'll probably jump in at various points when there's questions.
Please do. Thank you for the introductions, and thanks for having me. I should also add, that paper was actually a really fun collaboration with a whole bunch of people, each of whom was absolutely necessary for this work to come out this way. I learned a ton on the way, and I'm incredibly grateful to have had that opportunity to work with that bunch of people. But it is true, actually, that I'll try to find some cold water. I think I may have found a little bit. I should add as a caveat that this is not built like an academic talk, so it's a bit different from talks that I gave at conferences or so, in that it certainly is full of bold claims and has absolutely guaranteed insufficient evidence for pretty much all of them, I think. And so, believe at your own risk. So far so good. People often say, if it ain't broke, don't fix it. I think it's actually an incredibly useful, often very useful engineering mantra. But there's I think an alternative sometimes, or an alternative mode, which is if it ain't broke, well, let's try to break it. Let's see what's wrong with it, can we find kind of from first principles reasons why something that isn't broken actually, or doesn't seem to be broken, actually is failing in certain ways. And so maybe the subtitle to this talk could be something like 3 great reasons we should replace the transformer. And you would have never guessed number 3. And so since this is enough, or these were enough attempts at making jokes, even in the first 3-4 slides, the rest of the talk can be very serious. But maybe taking a step back, let's talk briefly about this kind of whole premature optimization versus first principles thinking, which I think is actually, premature optimization is really what this "if it ain't broke, don't fix it" tries to prevent. And I think that sometimes this idea of first principles thinking, Elon Musk talks a lot about it on and off, is potentially kind of a workaround in a certain sense, preventing you from, doing optimizations or going into a certain direction that you wouldn't necessarily have to go. And so, as an early example, I actually remember one time, as a preschooler. You know quite a bit of stuff as a preschooler, right? From experience, a lot of it, some not from experience, right? But you've probably learned that moving heavy stuff is hard. And you've also learned that explosions are really dangerous. And you've learned that they look like giant fireballs. Not all of this is true. And generally, at least I experienced that remote controlled cars are fast and awesome. And then the first time I kind of, somebody tried to explain to me how combustion engines work. There was this head-scratching moment, because what I heard was, well, cars are generally kind of built around this giant hunk of metal, and that giant hunk of metal is really only there because in the middle there are like small spaces in which there are explosions, and they're contained by this giant hunk of very, very heavy metal, and that tries to then channel all the force of these explosions into moving, an even bigger hunk of metal that is basically carrying this giant hunk of metal. That is the engine. And at least at the time, that seemed like a fairly backwards way of doing this. Obviously, I had no idea about kind of the energy in fossil fuels and all of that stuff, but it did seem odd. And I think it's actually not that different from the thought process that many years or decades later actually was what started this transformer project, because we did start with a few kind of first principles assumptions, namely, maybe most importantly, that it is possible or likely possible to compute good representations of some chunks of sequences in parallel. And what inspired us there most, I guess, is really that it seems like those tree structures that linguists often talk about when they try to formalize kind of the statistical dependencies between words and text are actually kind of largely right. So I personally believe they're almost never exactly right, but often, largely. And what that directly implies is, if indeed those statistical dependencies are often approximately tree-structured, then it should be possible to compute reasonable representations of chunks of text, for sure, of sequences of words in particular, in parallel, before you then kind of join these parallel threads of execution and then aggregate maybe new, more global representations from that. And another assumption we made is that training speed is actually really, really what is most crucial for model quality at the end of the day. And that the key bottleneck, at the time at least, was basically the length of the longest sequential computation. And so we kind of placed this bet that parallelization actually of this kind of sub-representation computation might be able to buy us much more than the computational cost that we had to expend in order to effectively marginalize out the dependencies, meaning basically assume all dependencies, right? So one interesting thing that this self-attention mechanism employed in every layer in the transformer does is it basically actually considers all pairs of stuff, right? And so in a certain sense, you could say it considers all dependencies, all possible dependencies, marginalizes those out, much more expensive than say considering only the true one, if there was such a thing and if you knew it, but seemingly worth it if as a result of that you can actually massively parallelize. And so in my mind, at least, that process was pretty similar kind of to maybe what made me scratch my head about cars and combustion engines, cars with combustion engines many years prior. And effectively, you know, the latter 2/3 of this talk I'm going to try to spend on a few maybe general areas in which I'm scratching my head about transformers in that same way.
Can I barge in?
Please.
So this is a super nice, like, historical kind of context about the origin of the transformer architecture. And I was wondering if you could expand a bit on the thing about this first principles approach, because I would say, like, at least for myself, it was kind of surprising that you could kind of remove the sort of somehow like temporal nature, which like as humans, when we read text, we tend to read, say, left to right or right to left, depending on which language you speak. And I was just kind of curious, like, was this something that you at Google kind of figured out from like linguists, or it's like it was really like taking a different perspective on the problem?
Okay, so it is a somewhat different perspective. There was a linguist involved. Well, actually, there probably were a few linguists involved. For me personally, the linguist that was involved most was my dad, computational linguist. So I had no choice. Right? The kind of a problem that runs in the family in a certain sense, and so, but it wasn't just, you know, what I took from him and others wasn't just the fact that there's maybe this kind of you know, often largely approximately right tree structure, but that in fact our ways or this model of thinking of language as something that is sequential is overly indexing on our representations of language. And so, you know, when we communicate, when we talk, we largely say words in sequence, except, you know, then we you know, often insert fillers. And we also, you know, often do this and so forth. So we interrupt ourselves the entire time. It's not exactly sequential, right? We do jump back. Yes, it's not like we can just fill in things, but we try, I think. And when reading text in particular, we actually can jump back. And I'm not an expert on this stuff, but as far as I know, it is not true that we always read in order. So probably, I mean, necessarily you can show we read more in order than not, because we eventually end up at the end of something, right? Of some long string of characters or words. But as far as I know, humans tend to actually jump back and forth a lot. Now that said, yes, we could go by the limitations of our own cognitive apparatus. But if we have a different one, and this makes a big difference, and probably I should have mentioned this, that actually, you know, what we were optimizing for wasn't software that runs on some accelerators or some silicon of our choosing. It had to run on the accelerators we had, and they looked, you know, largely like the ones that we still have today, except the ones today are even faster because they're evolving so fast. But they are just insanely good at doing these independent, simpler computations in parallel. And so if you really wanted to kind of improve utilization and what you could squeeze out from these accelerators, it just seemed to be the right direction to improve parallelizability. So that might be different from how you want to, or from how humans have evolved to process language, and probably is quite different, right? But yeah, it's just different hardware or whitware that has different strengths and weaknesses.
Awesome. Thanks for the context. And please carry on to tell us all the problems.
Okay. So right before I get to all the problems, I did want to spend maybe 2 more minutes or 3 on you know, why overall I personally would think it actually helped. And really, I think the key thing is this computational efficiency, specifically on today's typical accelerators. But there's another reason, and that has nothing really to do with, you know, the specifics of the model or the architecture, but really that once in a while, when something different comes along, it helps with momentum, right? It helps with competition, you know, friendly and all, but still, it really just helps to get people to contribute new, fresh ideas, or get people excited about stuff. Even if initially that excitement sometimes is disbelief or so, right? Or like I said, friendly competition. So it was like that the other way around. We had Facebook's convolutional seek-to-seek paper that that we in our what we thought last stretches of readying attention is all you need, that we first read that it came out then, and that had pretty good results. And so certainly, that nobody knew at the time, but that certainly pushed us and motivated us and so forth. And I think similar things happened afterwards. And in terms of momentum and fresh ideas and contributions that got people excited, Sasha Rush has this amazing The Annotated Transformer post, which when I saw it was just amazing and just really, really fun to see people do that kind of stuff. And I think that actually is often underestimated as contribution to kind of the community's reaction is underestimated as a contribution to what kind of makes this work or made this work in a certain sense. Okay, so nothing else? Well, there's this one other thing, and that's actually that decoupling the architecture and the parameters of the model from what you could call maybe the registration of the elements of the structures that the transformer ingests or produces actually allowed very easy adaptation to new and different input and output modalities, different kinds of structures, right? And effectively what it kind of did was it generalized this absolutely revolutionarily powerful seek-to-seek approach to something that's maybe a bit more like stuff to stuff, right? So technically you could say, oh, it's set to something, and then, or set to set, maybe even if you drop a bunch of, if you drop position representations and so forth. But ultimately, if you can encode the topology, if you wish, or the registration of these elements, right? These individual positions, or as they were called initially, that the transformer works on, then you can apply it fairly generically, not always efficiently, but fairly generically, and that in turn, made this guy show up, and with him, like this horde of other Muppets and friends and family of Bert. Initially, I guess, focused on language really, but then also spilling into vision and into this really, really impressive flurry of activity around self-supervised pre-training. So there was generative pre-training, which also uses the transformer in a maybe in quotes more traditional way, but exploiting this kind of flexibility, around the input and output structures that need not necessarily just be sequences in that sense anymore, but anything you could encode in a set somehow, just broadened or increased the efficiency of some of these self-supervised approaches, specifically masked or mask style, denoising autoencoders and related approaches. This has touched a whole range of different applications, including now biochemistry. So there is now PropBERT and DNA-BERT and AminoBERT that play a role in all sorts of different applications around or in proteomics, and also provided a great segue for me to kind of put in a shameless plug, maybe speaking a little bit to some of the things that we do at Inceptive, at least, which is as you heard in the introduction earlier, we're designing RNA, and specifically initially at least mRNA molecules that we try to design such that they have improved properties in desired ways, such as improved stability, that you might not have to deep freeze mRNA-based therapeutics or vaccines anymore, or that they might last much longer if you do. Higher protein expression, which could render it more effective and maybe applicable to a broader range of diseases. And it's just a fascinating, huge search problem with just ginormous spaces. So, even for the COVID mRNA vaccines, for instance, you have 10 to the 630 synonyms, mRNA sequences that would actually produce the same protein in our cells that we want produced for these vaccines. But it's also an incredible predictive modeling challenge, right? We don't understand most of these properties, meaning we don't understand how they work, and we don't even know if we know all the mechanisms. In some cases, we know we don't know all the mechanisms that kind of give rise to these properties or that impact them. And so we have very little hope of generating enough data in our lab for each of these properties of interest. And so really, self-supervised pre-training is at least one of the pieces of the puzzle that we hope to be applying in order to tackle problems around RNA therapeutics and vaccines.
Can I barge in again? Sorry. So this question you mentioned about we don't really understand the properties of these molecules. I mean, wasn't chemistry sort of solved by chemists in some sense, like 100 years ago? Could you maybe sort of expand a bit on what the challenges are?
Yeah, sure. So I'll try to be quick because there's still a lot coming. But basically, kind of true, yes. Chemistry kind of solved, but I would say there are aspects to some of these macromolecules, some of the biopolymers, RNA, DNA, that are not exactly kind of small molecule chemistry in the sense that, just like proteins, their structure, their 3D structure, their arrangement in space really makes a difference. And it can affect chemical properties, right? So depending on the arrangement, on the geometry effectively of the bonds relative to each other, you seem to get different behavior when it comes to things like hydrolysis that eventually degrades these macromolecules, for example. But that's just the chemical side. And we're definitely interested in that. But there's also the biological side. And there it gets even crazier because in the environment of cells, for example, right, there is an unknown set of players, some of which we know, many of which we don't, of enzymes, of proteins around that effectively have highly non-trivial effects on the properties of these molecules, like their biological stability, how long they last in cells, how much protein they express, and so on and so forth. So none of these properties really are kind of a function of just the molecule itself in question, but really a function of any number of different molecules around, which I guess also explains why end-to-end, very large-scale deep learning seems like a worthwhile thing to try. Whether it's going to work or not for, say, the specific application, of course, we don't know yet. There's some good indications that it can be useful, as we saw through AlphaFold and I guess some of the proteomics models that I mentioned earlier. But yeah, I guess the proof is still in the pudding.
Awesome. Thanks for clarification.
Sure. Okay, so with that, back to these first principles I was alluding to earlier, and how I personally think the status quo might actually be broken right now. And the first kind of cluster of issues that I see revolve around data. And this is maybe also the most important, given that data seems to, at the end of the day, always be the one thing. It's the one thing that always matters. It's not always the only thing that matters, certainly, but it definitely, machine learning is the one thing that always matters. And I guess I'm in good company with opinions like this, right? So Thomas tweeted a little while ago, a few years ago, I was mostly interested in models. Over time, he's seen his interest shift to data. And, it seems like we're slowly maturing. I agree. I do think it's a bit cyclical. These things go back and forth. When a revolutionary approach comes along and promises and delivers, like deep learning, massive improvements, then that becomes for quite a while, tends to become if it works, like it did in this case or does in this case, becomes the area of most or a lot of attention. But then what we've seen in the field a few times already is that as the rewards you reap by applying those methods and improving them start to slowly plateau, you can come back, you can usually come back to data in order to further improve stuff. And one interesting thing that I find odd is that, we still haven't found ways of end-to-end learning from samples from only the input or only the output distributions. So there are these highly, highly effective, but also pretty expensive pipeline heuristics. I would call them heuristics, like back translation or noisy student and lots of related methods. that effectively use learned models that are learned on smaller amounts of labeled data, so input-output pairs, in order to then turn either samples from only the input or samples from only the output distribution into input-output examples. And sure, you can do that, and it works great with some drawbacks, but still, it doesn't seem right. And there are architectures, in fact, several. One in particular I worked on together with a bunch of people called Kermit, that can be trained on input examples, output examples, and input-output paired labeled examples. But so far, it's not like they've actually shown even remotely the same kind of improvement as some of these, in quotes, heuristics. And I find that pretty odd, and that's definitely kind of a fairly obvious head scratcher in the sense that we see this data can help, but end-to-end in kind of end-to-end simplistic or simpler architectures, not pipelined schedules or so forth, we haven't been able to really reach the same improvements from that data. A slightly maybe more involved situation that is also very common actually is that we're still not able to learn end-to-end from unaligned data. And so there are many problems out there where the vast majority of training data, machine translation probably being the most prominent, where the vast majority of training data today actually comes from was produced by automated systems that were given ginormous amounts of input and output examples, but separately, input and output, not aligned. But knowing that there should be alignable pairs. And so in machine translation, for instance, work that I was involved in back in 2008 already, were recently far improved stuff, actually a variety of papers, have basically proposed these pipeline systems where you have one step in which you say, for instance, mine the web as a collection of unaligned monolingual documents, and you try to identify documents that are translated or that should be paired as training data for translation. And you do so oftentimes using a trained translation system or something quite similar. There's also been huge progress in unsupervised machine translation, which makes this assumption, right, that those links are not known. But that's all of those approaches are fairly specific, all of the ones I know of, are fairly specific to machine translation. And so what I haven't seen yet, and I'm confused by that, is a generic approach that applies across MT, but also question answering. There should be tons of questions out there that also have answers somewhere out there on the web that should be pairable, and comes with different problems, but also shares, I think, a lot of the problems that machine translation data mining has. Image descriptions is a similar one. There, I maybe see more of a reason for why we're in that situation, right? We've only recently started to really use training on otherwise unstructured, organically created descriptions or of images, alt texts, and similar in a way that really improves over the state of the art trained only on labeled data, certainly for image classification and object detection and friends. But still, it should be possible to get more data this way. And the list of problems for which this, at least I think, seems to be true, is actually quite long. Maybe again, kind of a specialization or an extension. Well, an extension of this could be that it need not be the case that they come from the same modality. Right, so usually today, labeled examples for one task, say translation, for instance, right, they're specific to one set or one pair of modalities. So there is now there's end-to-end speech-to-speech translation systems, and there are text-to-text translation systems, and so on and so forth. But a translation system that gets better if you show it, or when you show it, pairs of text, pairs of spoken translated sentences, pairs of images that depict, have half translations in them. Say, for instance, you take a photo of a restaurant menu in one language and then the translated version in another language, where instances or pairs of in all of these modalities actually improve one and the same system. And this is despite the fact that transformers have actually helped along the convergence of architectures across modalities. And I think one of the reasons why we've not seen this, certainly not much, is that oftentimes these joining these modalities in single models is done by effectively, adding heads that are then specific to those modalities. And unfortunately, we haven't yet figured out how to engineer these heads such that they only take care of things that are specific to the modality they're responsible for, and not of anything else. And that seems to be, I think, a remaining challenge that could address kind of this observation that we currently can't seem to be learning well from examples in different modalities, or the union of many examples from many different modalities each. But maybe kind of as an aside to this, how about multiple instances in a single modality, right? So instead of saying, we have text-text translation pairs, and we have spoken language translation pairs. How about we have, for some of those texts, multiple different versions, right? So we have maybe multiple ways of phrasing the same input sentence or the same output sentence. We have multiple ways of pronouncing a similar input or a synonymous input or output sentence. How about using all of those together at the same time? There is some interesting evidence from machine translation and speech recognition, actually, that this should help quite a lot. But if you look at things like computer vision problems, where it is also not uncommon that we have many images of the same scene or the same object, there it seems much less obvious how to actually then combine those in an elegant way. And I think actually, ultimately, my intuition would be that it hints at an underlying, more fundamental underlying problem that I'll try to kind of get closer to later in the talk. Okay, so we're technically already at the time I wanted to use initially for just the presentation. So I'll hurry up a little bit and maybe largely skip over this part, but it is also odd that in many problems or for many different tasks in computer vision and elsewhere, but in computer vision it's particularly pronounced, there are probably multiple different sources of data that could be particularly informative for learning models for this task. And one crass example is effectively things like, say, object detection, where clearly, today, most of those models are trained on two-dimensional annotations. Well, maybe annotations also, labels also in the 3 dimensions, but from annotations of two-dimensional inputs, images, or sometimes video. And plus some semantics, plus some labels, along with bounding boxes. But they don't actually ever consider non-semantic data describing geometry, even though it's actually relatively cheap to obtain this, right? So, unlabeled samples of fairly complex 3D geometries, obtained through LiDAR, can actually be created at fairly low costs. And I would say intuitively, if a model that tries to do object detection understands a ton about, not about semantics of objects in the real world, but about their geometry of common objects, right? What do cars, what's the shape cars generally have? What are the shapes bicycles generally have? That should help. But actually, so far, that doesn't seem to be something that we certainly not commonly do. And it also seems like pre-training for this kind of very orthogonal data that you want to jointly be able to learn from might not be quite the right paradigm. And so, maybe to sum up the data part, there's been amazing progress around pre-training and fine-tuning in this general paradigm. But transferring things across modalities still typically involves what I would call Franken models. So these are models where basically, depending on the modality, you turn some piece on and some other piece off, and you basically swap out pieces of the network more or less as deterministic functions of the modality of your input or the modality of your output. And as a result, but not only because of this reason, we're far from being able to utilize all the data that intuitively would seem relevant to a given problem. Say, like an object detection, we're not utilizing 3D geometry data. And given that data is by far the best overall, I would say, and most reliable way to improve models, that strikes me as a bit weird. And from first principles, I would say there's a lot of potential for changing things out. We'll get back to this at least a little bit later. But another area is indeed still efficiency. And I said earlier, well, transformers improve parallelization or parallelizability of some of the computation of representations of pieces of your input or effectively your output. And that's true, and I think that's really the single biggest reason why they help in many cases. But I actually think potentially the single biggest kind of source of inefficiency, if you wish, still largely remains to be tackled. And so, non-autoregressive machine translation made a lot of progress. Diffusion models have very recently made really impressive leaps. It's actually one of the really fun things for me to on occasion look at back in largely computer vision land or graphics also is what people are doing now with diffusion models. I think it's really cool. Addresses some of the aesthetic issues and also practical issues of autoregressive models very well. And in fact, if it wasn't for diffusion models, there would have been at least a fourth and maybe a fifth reason why we should replace transformers in this talk. But yeah, then despite global receptive fields that these transformers have, at least for many modalities, we actually know that the information stays largely local. So there's a paper by Lena Vojta and a few others that look at representations as they evolve throughout layers in transformers, and it seems like information doesn't travel that far, even though we have this global receptive field where every piece of your input or representation or your representation at least can talk to any other piece in every layer. And there's some obvious reasons for this, or more obvious reasons for this. One is the omnipresence of residual connections that provide a very strong bias for keeping representations, roughly aligned with the locality or the registration. Say in sentences, the position of a word that representation is computed for. But this also means that we allocate our compute resources approximately uniform across this registration, across, say, for example, if you consider images or video, spacetime. And okay, that doesn't sound like a terrible idea until you look at this image. And if you currently feed this image into a CNN or a vision transformer, it doesn't matter. Most of the flops expended look at blue sky, and only a small minority of them actually look at the bird and what kind of bird that might be. And that seems wrong. It seems bad enough for this image. But if you consider video with a non-moving camera, then this is actually true for most of the pixels most of the time in most of the videos, approximately, at least, minus some noise and maybe minute movements and so forth. But certainly for video, this seems to be a real source of inefficiency. And that's simply that the relevant information for any given task in these modalities, the relevant information content is often clumpy because that's how the world is. And this is true, at fixed resolution, fixed sampling rate, so fixed frames per second with a fixed resolution. It's certainly true, and sometimes much worse, otherwise, say when you have point clouds that are distributed very non-uniformly in space and space-time, space. And there have been some end-to-end approaches. The perceiver is an interesting one that try to tackle this problem, but so far they don't seem to be particularly efficient. They solve some of the issues, but they don't seem to be a real kind of complete answer to the efficiency aspect of this problem. And so, to me, I can't help it, but to me this smells like compression, right? The problem smells like it could be solved by compression. And so we know that utilizing lossy compression schemes that are actually aimed at human perception, not machine perception, can help quite dramatically. We've known it for quite a while. So could we just learn compression schemes suitable across a variety of tasks? And how would they be, if at all, different from today's learned representations that our neural networks evolve kind of layer by layer? Well, one key difference would be that they should either get faster over time as training commences, or they should spread information more uniformly as basically as training goes by and as the model gets better. And I think ultimately it in some way necessitates a change to the way we currently train these things, in part because we expect the sizes of things to change, right? So if we want to get the speed up, then the input size has to change. The input shape can't be constant. If we want information to spread more uniformly, then again, I would say one can argue that in our current kind of fixed batching scheme and so forth paradigm, this can't happen. Now, as I prepared this talk and prepared the slides, and in fact, this just happened earlier today. I was looking for one particular reference that highlighted one aspect of this problem, and had to ask Alexei Dosovitsky, with whom I had the opportunity to work on the vision transformer, and who's actually now at Inceptive as well, and asked him for this reference, and he didn't come back with a reference. He came back with the paper that hit arXiv on November 3rd that I hadn't seen. So much for arXiv sanity or insanity, that actually for at least some image tasks seems to provide a pretty good solution that basically kind of is along these thoughts and ideas. So yeah, look for that. It's pretty neat. I think I haven't read it in detail yet, but yeah. So maybe this is not one of those cases where from first principles it's still broken as of November 3rd. Okay, and so the last one that I'll have time, the last kind of block of things that I think are broken revolve around symbols, objects, this kind of stuff. And this is a super complex topic. I'm definitely not going to do it any kind of justice. Thankfully, there are some great reviews like the one from Klaus Greff and friends. But basically, the specific kind of potential area and currently active area of symbolic-ish object-laden representations that I would like to talk about shares one thing with all the other kind of instances of objects or symbolic-ish techniques in deep learning, namely that my overly simplistic view of them is that they really are merely efficiency hacks that we should learn, and that they don't do us any good really, other than speeding stuff up. Now, this is definitely a somewhat controversial opinion, but if we look at only symbols in say input and output representations, it's not too difficult to make that claim at least a little bit. Okay, so a thought experiment, right? Usually we represent text, for instance, as a sequence of tokens, maybe down to characters or so, right? But this actually comes at a significant cost in expressivity. We take this for granted, but we certainly can currently train text models that understand this thing. Not in full, at least, right? Maybe if you were to now kind of add formatting tags and stuff like that, maybe for this case it would work. And maybe you could claim, okay, fine, but that seems kind of unimportant, super rare, and whimsical, right? But then let me ask you, why is it that I can only have new emojis once a year? And why do they have to be selected by some committee? Right? We recently had this case actually in practice where there's a DNA emoji, but there's no RNA emoji. So we thought, oh, can't we make the claim now that RNA is something, mRNA in particular, that's on everybody's mind? Can't we just ask them to get us an RNA emoji? And we were about 3 days too late for the deadline, and reaching out to the Unicode consortium didn't help. I understand why and so forth, but there are definitely some drawbacks to requiring these kinds of organization that stem ultimately from the fact that we want to use symbols to encode this stuff. And it gets pretty bad once you leave kind of the Latin script dominated parts, and you encounter that, yes, in fact, there are scripts to this day where proper typesetting on computers doesn't really work. Mongolian, I think, is an example of that. To be honest, I don't know exactly how common the phenomena are that are not well expressed in today's typesetting systems. So I can't really kind of estimate the gravity of these issues, but it's definitely the case that we're losing out in terms of our richness of representation of things like text by using these kinds of symbols. So what if instead of doing that, we presented it, across many tasks in a more generic form? Say, as the pixels of an image into which we've rendered the text. And that's something that we've actually tried for machine translation and wrote a little paper about a while ago, Alman. But obviously that's terribly inefficient, right? So now instead of using these symbols that we hand engineer, like emojis, like Unicode at the end of the day, now we have pixels. They usually require, you need many more pixels, certainly if you want to express kind of these rich formatting and graphical phenomena. And so with today's machinery, that's terribly inefficient. But let's assume for a second, we actually had some really efficient learned and compressed implicit representation. We could potentially get it down all the way, or not all the way, but fairly close to kind of those symbolic representations. And they might actually remain richer. And it's not entirely clear that we couldn't, in some cases, go below that, because text also tends to be compressible, even losslessly. And so actually, it seems like this idea that effectively seems obvious for images and video might even ultimately help with efficiency if it's applied to text, at least if you have it in sufficiently large amounts. So to make a very long story and very, very kind of hypothetical story somewhat shorter, I wonder what would models look like if we reduce the reliance on external symbolic representations, on hand-designed, crafted symbolic representations, at least for input and output. And if we compensated for the efficiency loss by generically or with generically learned dense implicit representations, and then on the way, increasingly unified, use this kind of transition to increasingly unify the shapes of different modalities, right? So we've now said that maybe images and text should or could look very much alike. I don't know exactly what this would look like. I have some guesses, but they're definitely too half-baked to put them even on these slides. But maybe we could also apply this to other modalities as well, and then maybe even this multiple heads, input and output heads hydra problem would go away, right? Could we then actually just stuff this all into one single giant neural network? Not one where individual pieces have to be turned on or off depending on what the modality is at any given moment, but where it's really just the same very dense, highly optimized architecture, same set of parameters. You might not even need elements anymore, or maybe they're always canonical, right? Kind of fixed length up to a certain degree or fixed size. So anyway, I wonder what that would look like. And I actually feel like, maybe using at least some of these, as half-baked as they all are, observations and quotes, first principles, head-scratching moments, to inspire thought about ideas around what those models could look like, I personally think could be quite interesting.
Awesome. Thanks a lot, Jacob. That was a super nice talk. It's not every day that we get to see the kind of like deep questions, about transformers being exposed this way. So very nice. I think we have time for a couple of questions. There's one which is perhaps a little bit technical, but let's see how we go. So it's there's a typo, but can transformers be used to find which code snippets in one language are similar to another? So, if you've got Java and Python, and do you think, graphical neural networks would be a solution? And I think what this question is getting at is a little bit this thing about like, you emphasized a lot machine translation and alignment and this kind of stuff. And, do these problems also occur when we deal with source code?
Super interesting question. So let me think. Basically, so I would say, the simple, straightforward answer is yes. Transformers could definitely be used for something like this. One interesting question is, how would you define what it means for snippets of code to be the same? And a very pragmatic definition that one could potentially operationalize for creating data around this is to run the code and see what happens. And if you then end up with either the same result or the same behavior, in quotes, then maybe you, at some point, if that happens often enough, you want to say, yeah, these are reasonably similar. And in the process of doing this, basically generate instances, increasing numbers of instances, and instances of potentially increasing complexity, right? If you start doing this for single instructions and then you add stuff, you might even with fairly unguided search procedures get to a stage where you can just create training data for a model that then might look like something like a seek-to-seek model, but it could also look like these I guess, what do you call them? Siamese or two-tower models that are effectively trained to compare different instance or input representations for multiple instances. GNNs in particular are basically making use of the fact that code has this much more stringent structure than natural language or observations of the natural world around us. I mean, certainly in many cases, I could imagine could help with efficiency. Would it dramatically transform our ability to identify whether these two things, whether two code snippets are the same? That I'm not so sure about, because ultimately, whether they're the same or not, I guess, doesn't have as much to do with, say, their abstract syntax trees and how those relate to each other. Where the crispness of GNNs would help, as it does with the semantics of the code. Right? The subtle issues are you call two different library functions. They're defined to be mostly the same, except for some subset of the inputs, and hence you ultimately have to, if you want to do it, just from with zero other knowledge, you basically have to figure this out. Ultimately, I guess also made further problematic because there are many different ways of computing any one thing, and as a result, even going all the way down to executed instructions on a given CPU or so, or a given chip, whatever it is, might not actually conclusively answer your question unless they happen to be exactly the same. Right? So if they compile to the same bytecode or the same natively executed instruction sequence, sure, then you can, but I don't think that's a likely event.
Cool. And maybe one more question. Yeah, thanks a lot. One more question would be, in this sort of landscape of challenges you mentioned, so things with symbolic representations, lossy compression, and so on, which of these do you think is like let's say, the most important, so to speak? If you had to rank somehow these problems, which ones keep you awake at night, maybe is the other way of putting it?
So I actually think they all are. I really think that they all are, not exactly, but they all are roughly different sides of the same coin. So our difficulties in learning, interchangeably from different modalities, they stem from the fact, I think, maybe overly simplified, but I think they largely stem from the fact that we have this heads problem, that basically we don't have a neural network into which we can actually input these efficiently, without swapping out some sets of parameters or maybe some kind of structural pieces. And so that you could address by having in a certain sense, a representation at a meta level that is able to express things in all of these modalities. And that you could get by learning kind of these compression schemes if you learn them across many different modalities. And hence, I guess I also think that ultimately our only way of potentially getting rid of these symbols, which yes, I think they currently, they are very pragmatic heuristics for improving efficiency, but we don't know how optimal they are, and they're certainly not sufficient in order to express everything we'd like to express. But I would guess they're not optimally efficient either. And there again, I think having these kinds of learned implicit representations is a reasonably good kind of general direction for trying to address the potential inefficiencies, but also kind of broaden or increase the expressivity of models for some of these modalities. And so in a certain sense, I think they all kind of belong to each other. Doesn't mean that and it's certainly unlikely that the easiest or kind of the most direct potential solution for addressing any single one or any single very specific subset of these, that they would at all look, similar to each other. That I don't think is the case. But maybe kind of in the limit, if you want to generally solve all of these, it might be that actually they share one and the same solution.
So are you sort of telling us that the future may involve some sort of not maybe radically different architecture, but some that there is life beyond transformers in some sense?
I actually think the architectures will increasingly get simpler and simpler and simpler, and they will increasingly look very much like, you'll be able to tell the architecture from the hardware it runs on. And so ultimately, I think to me personally, the big lesson that I learned in the vision transformer work is that these patches that we use there have nothing to do with the images. They're not chosen based on the image. They're fixed. So why is it that some patches work better than other patch sizes and so forth? It's because they have slightly different computational trade-offs. It has nothing to do with the nature of the images, as far as I can tell. Maybe in extreme cases that could happen. You could imagine certain distributions of images and certain kind of patch sizes that just make it harder or make it easier. But by and large, across kind of the universe of images and the universe of possible patch sizes, or the space of possible patch sizes, what matters, I think, is how well they are suited to the underlying hardware. And so my guess is what we're going to see is that the architectures will look more and more boring, which I think is great, because architecture engineering tends to be this kind of, black magic alchemy that more often doesn't work than it does. And ultimately, I think, basically we'll use more and more uniform necessarily. Will necessitate more and more similar and uniform representations that have, where, for instance, also the relation between representation size, if you wish, and compute budget becomes much, much less direct. Right? So right now, if you want to expend more flops on the same image, right, take more patches of the same size, and you're going to do exactly that. And then that doesn't get better, at least from our experiments. That doesn't seem to get better, because somehow your additional patches now overlapping or whatever add kind of more, in a certain sense, more interesting detail. It just gets better because you add more flops, as you would kind of expect. But that it shouldn't be that kind of your way of computing your initial input representation, if you want to think about it that way, is kind of the screw that you use in order to adjust the expended compute up or down. If anything, it should be kind of how information rich given the task or for the task a given input might be. And ideally, ultimately thinking of us humans, a little bit at least, maybe what really should necessitate how much compute you spend is how much time you have. If I have a ton of time to compute the answer for a given input, take the time. I mean, assuming the energy comes for free and in a sustainable manner and so on and so forth. But why not take longer? But if you have to make a decision really quickly because the product calls for it in that situation, ideally the model is able to at least give you a reasonable guess in much less time, with much less compute. And so I feel like that's what we should actually strive for, like anytime algorithm style inference, if you wish. Anyway, so yeah, long story short, I think architectures will hopefully become less boring and just ideally suited to the hardware they run on, and in a certain sense, the remaining work to get us there is I think in figuring out how to unify and how to make effective and efficient the representations that we use.
Awesome, thank you. I think we've run out of time, so thank you once again for sharing your deep knowledge with us and the community. And it's been a pleasure. So I hope,
thanks for listening.
Hope next time we ask you, all these problems are solved.
Well, we'll see. I mean, given that paper that came that I only just saw earlier today that came out on November 3rd, who knows? With that pace.
Great. Thank you very much, Jakob.
Thank you.
Thanks.
Cool. So
Cool.
that's the end of day
Thanks
one.
a lot. Yeah, thanks a lot for following this event today, everyone. We have a second live event tomorrow at the same time. It begins at 8 a.m. PST, and it's going to end around noon PST with the Hugging Face team, more focused on giving you technical talks on how to fine-tune a transformers model either with Pytorch TensorFlow, and how to upload the model to share the community, and how to build a space to build a nice demo out of it. And so it's mostly members of the Geek Face team, as I said, as well as a guest speaker from the AWS SageMaker team, and another speaker from the Radio team. So thanks a lot for following today, and see you soon.
Bye, everyone. See you tomorrow.
Bye.